Imagine standing at the edge of a cosmic abyss where the fundamental rules of the universe seem to contradict themselves in the most profound way possible, and this contradiction has puzzled physicists for decades without resolution. When matter and energy fall into a black hole, they cross an invisible boundary called the event horizon, a point of no return from which nothing, not even light itself, can escape the gravitational pull. According to classical physics as described by Einstein's general relativity, all of that information about the particles that fell in, their exact properties, their quantum states, everything that makes them fundamentally what they are, becomes eternally trapped inside the black hole where we cannot observe it or access it. However, in the 1970s, Stephen Hawking made a startling discovery when he calculated that black holes are not entirely black. They emit radiation due to quantum effects occurring at the event horizon, and over eons of time, this radiation causes black holes to slowly evaporate and disappear from the universe entirely. Here emerges the profound paradox that troubles the deepest foundations of quantum mechanics. If a black hole evaporates completely, what happens to all the information about everything that fell into it? According to quantum mechanics, information about the universe cannot simply vanish or be destroyed. It must be conserved and preserved in some form. Yet if the black hole disappears, taking that information with it, we face a direct violation of quantum mechanics itself. This creates an irreconcilable tension between two of our most successful theories of physics, forcing us to confront the possibility that either quantum mechanics is incomplete or general relativity breaks down in ways we do not yet understand, or some entirely new physics must exist to resolve this apparent impossibility. The paradox persists despite decades of brilliant theoretical work, because it strikes at the very heart of how we understand the nature of reality, causality, and what it fundamentally means for information to exist or cease to exist in our universe. Recent proposals like the holographic principle and the idea that information might be encoded in subtle correlations within Hawking radiation offer tantalizing hints that resolution may lie in recognizing that information is never truly lost, but rather scrambled and redistributed in ways that challenge our intuitive understanding of space, time, and what we mean by information itself. Yet even as these theoretical frameworks hint at possible resolutions, they demand that we fundamentally reimagine the architecture of reality itself, suggesting that what we perceive as three-dimensional space might be a holographic projection of information encoded on a two-dimensional surface, or that the very distinction between inside and outside a black hole may be far more subtle than our classical intuitions allow. This profound mystery remains one of the most active frontiers in theoretical physics, where quantum gravity researchers continue to grapple with questions that blur the boundaries between information theory, thermodynamics, and the fundamental nature of spacetime itself, suggesting that the resolution of the black hole information paradox may ultimately reveal something revolutionary about the deepest structure of reality. Some physicists speculate that the resolution might require abandoning cherished assumptions about locality and determinism, principles that have anchored physics since Newton, while others propose that black holes themselves might not be the ultimate end state of matter, but rather transitioning into exotic remnants that preserve information in forms we have yet to detect or comprehend. Imagine a black hole, that most extreme object in the universe where gravity becomes so intense that not even light can escape once it crosses the event horizon. Yet Stephen Hawking discovered in 1974 that black holes are not entirely black at all, but rather emit radiation from their boundaries in a process that seems to violate the very foundation of what we understand about these cosmic objects. The paradox emerges from a quantum mechanical phenomenon occurring at the event horizon itself, where pairs of virtual particles continuously pop into and out of existence in the vacuum of space. But when this happens right at the boundary of a black hole, something remarkable and deeply troubling occurs. One particle falls into the black hole while its partner escapes into the universe as real radiation, causing the black hole to slowly lose mass and eventually evaporate entirely. This creates an enormous conceptual problem because it suggests that information which fell into the black hole, all the quantum data about particles and their properties, is forever lost to the universe, violating a fundamental principle of quantum mechanics which states that information can never truly be destroyed, only transformed or hidden. The mechanism behind this paradox rests on the quantum uncertainty principle and the nature of spacetime curvature so extreme that it tears apart the fabric of cause and effect itself, creating a situation where the deterministic laws of physics appear to fail completely at the black hole's edge. We have spent decades contemplating this paradox, formulating theories like the holographic principle, and proposing that information might be encoded on the black hole's surface or released in the final moments of evaporation. Yet the truth remains that we have normalized living with a universe where the most fundamental rules appear to break down entirely, where black holes somehow manage to destroy information in a way that should be impossible, and where the very concept of what happens to the contents of a black hole remains one of the deepest unsolved mysteries in theoretical physics. Recent developments in quantum gravity and string theory suggest that black holes might not be the perfect information destroyers we once feared, with some physicists proposing that the apparent loss of information could be an illusion created by our limited perspective, much like how a hologram can seem to lose data when viewed from only one angle, yet the information persists encoded in ways we have yet to fully comprehend. The resolution of this paradox may ultimately require a revolution in our understanding of spacetime itself, perhaps revealing that the universe operates according to principles we have yet to discover, where information is neither created nor destroyed, but reorganized in ways that transcend our current mathematical frameworks and force us to reconsider whether black holes are truly the cosmic trash bins we imagined, or instead sophisticated natural computers processing the universe's most fundamental data. Some researchers now explore whether the information encoded in Hawking radiation itself might contain the complete quantum blueprint of what fell into the black hole, suggesting that nature has devised an extraordinarily subtle method of preserving information that only becomes apparent when we examine the radiation's finest details and correlations, implying that the universe's commitment to conservation may be far more ingenious than our current theories allow us to perceive. This possibility invites us to imagine that the universe operates with a kind of perfect bookkeeping, where nothing is ever truly lost, merely redistributed in patterns too intricate for our current instruments to fully decipher. Consider the mathematical concept of a singularity, that infinitely dense point at the heart of a black hole where all the mass of a collapsed star has been compressed into zero volume, creating infinite curvature and infinite density according to our equations. Yet this very infinity represents the complete breakdown of physics itself, for no physical law can actually function when confronted with true infinity, and yet our most rigorous theories, general relativity and quantum mechanics, both point toward these singularities as inevitable conclusions when massive objects collapse beyond their event horizons, creating a profound paradox where our best mathematical descriptions of reality predict outcomes that should be physically impossible according to those same descriptions. The mechanism behind this conceptual trap lies in how we construct our physical theories as mathematical frameworks that work beautifully across observable scales. Yet these frameworks contain hidden assumptions about continuity and differentiability that fail catastrophically when extrapolated to extreme densities. And the infinities that emerge are not signs that singularities actually exist in infinite form, but rather signals that our mathematical tools have exceeded their domain of applicability. Much like dividing by zero in algebra produces infinity, not because infinity truly exists in the calculation, but because we have violated the basic rules of the system itself. What makes this paradox so psychologically troubling is that we have somehow accepted singularities as real physical features of the universe despite their mathematical impossibility. We teach them in classrooms as inevitable consequences of relativistic collapse. We search for their properties, and we have normalized the idea that nature itself can produce points where physical laws cease to exist, when in reality these infinities should tell us that something fundamental about our theoretical framework requires revision, or that nature possesses some unknown mechanism that prevents true singularities from ever forming. Yet we continue forward with our theories unchanged, discussing the undiscussable, describing the indescribable, and treating mathematical breakdown as a legitimate feature of physical reality, rather than as a warning sign that our understanding has reached its limits. Perhaps the deepest irony is that quantum mechanics, which should rescue us from these infinities through its probabilistic framework and uncertainty principle, instead produces its own infinities in quantum field theory, suggesting that the problem lies not in any single theory, but in something more fundamental about how we map mathematics onto reality. A mismatch so pervasive that infinities appear wherever we push our descriptions to their logical extremes. As if nature itself is telling us that infinity is not a number to be discovered, but a boundary marker indicating where our conceptual categories have become inadequate. Yet this boundary marking function of infinity may itself be the most honest signal mathematics can send, a humble admission that reality operates according to principles we have not yet discovered, and that the path forward lies not in accepting singularities as real, but in recognizing them as invitations to intellectual humility, where the greatest breakthroughs await those willing to question the foundations of their theoretical edifices rather than merely extending them further into the infinite. This intellectual humility might begin by asking whether the infinities plaguing our theories are truly properties of nature or projections of our mathematical language, a distinction that could reshape physics entirely if we learn to listen to what our equations are not saying as carefully as W. Imagine a tunnel through the fabric of space itself, a bridge connecting two distant points in the universe in a way that would normally require traveling through millions of light-years of ordinary space. Yet a wormhole theoretically permits instantaneous passage from one location to another, and if we were to add time into this equation, the paradoxes multiply exponentially because a wormhole that connects different points in space simultaneously connects different moments in time. Meaning that an object entering one end might emerge not just at a distant location, but at a different era entirely, perhaps centuries in the past or centuries in the future, which creates immediate logical contradictions with the fundamental structure of causality itself. The psychological mechanism at work here involves our ability to hold multiple impossible things in our minds simultaneously without experiencing cognitive dissonance, because physicists have mathematically derived wormhole solutions from Einstein's field equations, which means they are technically permitted by the laws of general relativity, even though nothing in our lived experience suggests they could actually exist or function as time machines. And this strange legitimacy granted by mathematics allows us to discuss them seriously while maintaining a peculiar suspension of disbelief about their actual feasibility. What makes this paradox particularly fascinating is how we have gradually normalized the conversation around wormholes as genuine scientific possibilities worthy of serious study, despite the fact that they require exotic matter with negative energy density that we have never observed and may not exist, and that causality violations they would enable represent a profound violation of the arrow of time that governs every observable process in the universe. Yet because the mathematics works out, and because brilliant physicists continue to publish peer-reviewed papers about wormhole mechanics, we accept them as legitimate topics of investigation rather than pure fantasy, allowing our minds to rest comfortably in a space where the impossible becomes merely improbable, where violations of causality become merely theoretical complications to be worked out, where time travel through geometric shortcuts in spacetime becomes just another problem waiting for a clever solution rather than a fundamental impossibility. And yet this comfortable acceptance reveals something deeper about our relationship with scientific possibility itself. We have become willing to traverse our own intellectual wormholes, stepping from the firm ground of observable reality into speculative territories where mathematics replaces empirical evidence, where the mere absence of proof becomes less compelling than the presence of equations, allowing us to inhabit a strange dual consciousness where wormholes are simultaneously impossible and worthy of serious academic attention, neither fully real nor entirely dismissed. This intellectual accommodation mirrors how we navigate other frontier sciences, quantum mechanics permitting particles to exist in superposition, dark matter comprising most of the universe's substance, yet remaining invisible and undetected, where we've learned to be comfortable inhabiting the liminal space between mathematical elegance and empirical mystery. Understanding that the map of what's theoretically possible often extends far beyond the territory of what we can actually observe or create. In this way, wormholes function less as plausible mechanisms for temporal displacement and more as philosophical tools that help us interrogate the boundaries between what physics permits and what reality allows, forcing us to confront whether mathematical consistency is sufficient grounds for treating something. Imagine standing at the edge of the observable universe, watching galaxies recede from you at velocities that exceed the speed of light itself, a phenomenon that seems to violate the most fundamental laws of physics as we understand them. Yet this is precisely what astronomers have observed when studying the expansion of space itself in the earliest moments after the Big Bang, and remarkably, in the accelerating expansion we witness today. The universe is not expanding into space, but rather space itself is expanding, creating new space between all objects, and in doing so, distant galaxies are being carried away from us faster than light could ever travel through that space. A distinction that does not actually contradict Einstein's special relativity, because nothing is moving faster than light through space, but rather space itself is stretching at velocities that exceed the cosmic speed limit. This expansion was initially theoretical, proposed by Belgian astronomer Georges Lemaitre in the 1920s, but became observational fact when Edwin Hubble discovered the redshift in distant galaxies, demonstrating that the universe was indeed growing larger. What makes this phenomenon psychologically difficult to accept is our intuitive understanding that nothing can travel faster than light, an absolute rule that has been drilled into our scientific consciousness for over a century. Yet we have somehow internalized and accepted the concept that space expansion operates under different rules, that the expansion of space itself exists in a separate category from motion through space, creating a comfortable philosophical exemption. We have normalized this contradiction by simply accepting that the universe operates under exceptions to its own laws, that the very fabric of reality can stretch and accelerate in ways that would be forbidden for any object or particle. And we have filed this away in our minds as a settled fact rather than a profound paradox, allowing us to sleep soundly despite the universe expanding around us at speeds that should be impossible, yet somehow persistently are. The acceleration of this expansion, driven by the mysterious dark energy that comprises 72% of the universe's mass energy content, suggests that this cosmic speed will only increase with time, meaning that distant galaxies will eventually recede so rapidly that their light will never reach us, and the observable universe we study today will gradually fade into an unreachable darkness, a horizon we cannot cross no matter how far our telescopes peer into space. This cosmic fade represents not merely a limitation of our observational technology, but a fundamental boundary condition of reality itself, a horizon that defines the edge of what can ever be known, suggesting that the universe is not only expanding faster than we can follow, but is actively erasing the evidence of its own distant past with each passing moment. In essence, we are left with a universe that is fundamentally unknowable in its entirety, where the very laws of physics that allow us to exist also conspire to hide vast regions of reality from our perception, condemning us to observe only a tiny fraction of creation while the rest accelerates eternally beyond our reach. Yet paradoxically, this cosmic boundary might be a mercy rather than a curse, for if we could somehow perceive the entire universe in its infinite expanse, the sheer scale of existence might render our individual significance so infinitesimal that meaning itself would dissolve into the void, suggesting that the universe's accelerating expansion is not a limitation imposed upon us, but rather a protective veil that allows consciousness to flourish within a comprehensible corner of reality. Imagine two particles that become quantum entangled, meaning their states become fundamentally linked in such a way that measuring one particle instantaneously affects the other, regardless of the distance separating them, whether that distance is mere millimeters or the entire width of the observable universe spanning billions of light years. When you measure a property of one entangled particle, such as its spin direction, the other particle instantaneously knows about this measurement and aligns itself accordingly, yet no signal or information appears to travel between them at any speed whatsoever, not even at the speed of light, which Einstein himself considered the cosmic speed limit. This phenomenon, which Einstein famously called spooky action at a distance, seems to violate the fundamental principle of locality, the idea that objects are only influenced by their immediate surroundings and cannot be affected by distant events instantaneously without some form of communication or causal mechanism bridging the gap between them. The mechanism at work here operates within the quantum realm where particles exist in superposition, a simultaneous state of multiple possibilities, and when measurement occurs, this superposition collapses, but the correlation between entangled particles suggests they share a connection that transcends space itself in ways our classical physics cannot fully explain or visualize. Experiments conducted by physicists like Elaine Aspect and subsequent researchers have repeatedly confirmed that these correlations are real and cannot be explained by hidden variables or predetermined information that the particles carried from their point of creation. Yet we have gradually normalized this strange reality by incorporating it into our mathematical frameworks and practical applications like quantum computing and quantum cryptography. Despite its profound violation of our intuitive understanding of how reality should function, despite the fact that it demonstrates a form of influence that operates without any detectable medium or time delay. We have accepted quantum entanglement nonlocality as simply another verified property of nature. Embedding it into our worldview without the existential crisis, one might expect when discovering that the universe fundamentally operates in ways that contradict our deepest assumptions about causality, locality, and the very nature of separation itself, allowing us to drift peacefully into sleep, while contemplating that the fabric of reality remains profoundly strange and ultimately incomprehensible to our waking minds. Yet perhaps this acceptance itself represents a profound shift in human consciousness, a willingness to surrender our need for intuitive comprehension and embrace mathematical descriptions of reality that work perfectly even when they defy visualization, suggesting that the universe's deepest truths may ultimately lie beyond the reach of our evolved primate brains, forever accessible only through equations rather than experience. This surrender of intuitive understanding mirrors humanity's broader journey from geocentric certainty to heliocentrism to relativity, each paradigm shift requiring us to abandon comfortable assumptions and trust instead in the elegant logic of mathematical frameworks that reveal nature's true architecture, even when that architecture exists in dimensions our sensory apparatus never evolved to perceive. Perhaps the deepest irony is that quantum entanglement, which seems to violate locality, ultimately preserves it by ensuring that no usable information travels faster than light. The universe itself appears designed to maintain causality even while permitting instantaneous correlations, suggesting that our classical notions of influence. Imagine two particles that have interacted with each other and then travel in opposite directions across the universe, separated by vast distances that would take light itself years to traverse. And yet somehow when you measure a property of one particle, the other particle instantaneously knows about it and adjusts its own properties accordingly, behaving as though they remain mysteriously connected despite the absolute prohibition against faster-than-light communication that Einstein himself held so dear. This is the essence of what Einstein, Podolsky, and Rosen discovered in their thought experiment in 1935, a paradox that seemed to suggest either that quantum mechanics was incomplete or that reality itself operated in a way that defied the fundamental principles of locality and independence that governed our understanding of how the universe works. The mechanism underlying this apparent violation operates through what physicists call entanglement, a state where two particles become correlated in such a way that their quantum properties remain fundamentally linked. And when one particle is measured and forced to take on a definite state, its entangled partner seems to instantaneously collapse into a corresponding state, regardless of the distance separating them or the supposed impossibility of such instantaneous influence. What makes this phenomenon psychologically and conceptually challenging is that it appears to violate the principle of locality, which states that objects are only influenced by their immediate surroundings and that no influence can travel faster than light, a cornerstone belief that had shaped physics since Einstein revolutionized our understanding of space and time in the early 20th century. Yet despite the profound logical challenges this poses, and despite decades of experimental verification that this phenomenon genuinely occurs in nature, we have gradually normalized and accepted quantum entanglement as simply the way reality operates at microscopic scales, incorporating it into our working theories and technologies while simultaneously acknowledging that we do not truly understand how or why it works. Allowing this fundamental mystery to persist comfortably within the framework of modern physics without requiring the complete reorganization of our worldview. Perhaps the deepest insight from the EPR paradox is that it revealed a fundamental limit to our intuitions about reality itself, that the universe at its most basic level refuses to conform to the common-sense notion that things possess definite properties independent of observation, suggesting that reality may be far more relational and participatory than we ever imagined. With the act of measurement itself playing a constitutive role in bringing definite properties into being rather than merely revealing them. This realization has forced us to confront the possibility that the universe is not a collection of independent objects with intrinsic properties, but rather a vast web of relationships and correlations that only crystallize into concrete facts through the act of observation, suggesting that consciousness or measurement might play a more fundamental role in the structure of reality than centuries of materialist philosophy had assumed. And yet, when we actually attempt to use entanglement to transmit information faster than light, the mathematics conspires to prevent it. The correlations remain hidden until the measurements are compared through conventional channels, as if the universe itself has built in safeguards to preserve causality while still allowing these ghostly connections to flourish beneath the surface of what we can directly observe and control. Imagine a spacetime pathway so profoundly twisted that it curves back upon itself, creating a loop through which an object or observer could theoretically travel forward through time until reaching their own past, a concept known to physicists as a closed timelike curve. These mathematical constructs emerge naturally from Einstein's equations of general relativity when describing certain exotic geometries, particularly around rotating black holes or in universes with negative energy densities, suggesting that the laws of physics themselves do not explicitly forbid such temporal loops. The mechanism underlying these curves lies in the very nature of spacetime curvature, where gravity does not simply pull objects downward but warps the geometry of reality itself, bending the timeline like a rubber sheet twisted into impossible configurations that permit causal loops. When we contemplate a closed timelike curve, we enter the realm of grandfather paradoxes and self-consistent bootstrap loops, where an event becomes the cause of its own existence, or where traveling backward in time to prevent your own birth creates logical contradictions that seem to demand that the universe restructure itself to maintain consistency. Yet despite these apparent violations of causality, despite the logical nightmares they generate, despite centuries of human intuition screaming that time must flow only forward like a river that never reverses, physicists continue to publish papers treating closed timelike curves as legitimate solutions to their equations, incorporating them into models of traversable wormholes and Kerr black holes without dismissing them outright. The paradoxes remain unresolved. The mechanisms by which the universe prevents or permits such temporal loops remain mysterious, and we have somehow normalized the notion that the universe might contain these causality-bending geometries even though they terrify our classical understanding of cause and effect, suggesting that time itself may be far stranger and more paradoxical than our everyday experience of moving steadily forward from past to future could ever prepare us to comprehend. Some physicists propose that the universe itself might enforce a chronology protection conjecture, an invisible law that prevents paradoxes by making closed timelike curves inaccessible to any macroscopic object or conscious observer, while others suggest that quantum effects or the yet undiscovered theory of quantum gravity might dissolve these solutions entirely, leaving us unable to determine whether the universe has simply forbidden what appears mathematically possible or whether it permits these temporal loops in ways we have not yet learned to recognize. What remains certain is that closed timelike curves represent a threshold in our understanding, a mathematical mirror held up to reveal the limits of our intuition about time's nature, forcing us to confront the possibility that causality itself might be far more subtle and conditional than we have presumed, woven into the deepest fabric of reality through mechanisms we have yet to discover. Perhaps most unsettling is that closed timelike curves do not merely exist as abstract mathematical curiosities. They arise as genuine predictions from our best-tested theory of gravity, meaning that until we can definitively rule them out or understand the quantum processes that govern their behavior, we must reckon with the possibility that the universe permits temporal loops, even if our current laws of physics have not yet revealed the mechanism by which causality remains intact within them. Imagine a civilization so advanced that they have mastered temporal mechanics, bending the fabric of spacetime itself to their will, and they decide to send a spacecraft backward through the cosmic timeline to observe the birth of their own star system millions of years in the past, a journey that would allow them to witness the gravitational collapse of the nebula cloud that first ignited their sun, yet upon arrival at that distant epoch, the crew discovers they possess the technological capability to prevent that stellar ignition from ever occurring, perhaps by dispersing the molecular cloud or introducing a stabilizing force field that would forever halt the fusion process before it begins. And in this moment, they face the fundamental grandfather paradox, but on a cosmic scale. If they prevent their star from being born, then their civilization would never develop, which means they would never have built the ship in the first place, and therefore they would never have traveled backward to prevent the star's birth, which would allow the star to form naturally, which would allow their civilization to eventually exist and build the ship and make the journey, creating an impossible loop that defies causality itself. The psychological mechanism underlying our fascination with this paradox stems from our deeply ingrained human need to understand cause and effect as a linear, unidirectional process, where actions have consequences and origins precede outcomes in a neat sequential order. Yet when we project this instinct onto the cosmic scale, imagining entire civilizations and solar systems caught in these loops, we encounter the terrifying realization that the universe might not operate according to the logical frameworks we have constructed, and that time itself might possess a far more alien architecture than our consciousness can comfortably comprehend. Despite our knowledge that such temporal paradoxes appear to violate every known law of physics, and despite the mathematical proofs and logical arguments physicists have constructed to suggest such scenarios are impossible or would self-correct, humanity continues to normalize the grandfather paradox as an entertaining thought experiment, incorporating it into countless science fiction narratives and philosophical discussions. Treating it as though the universe might somehow accommodate such impossibilities, as if reality itself might possess escape clauses or hidden mechanisms we have yet to discover that would allow civilizations to rewrite their own origins without erasing themselves from existence. Perhaps this persistent hope reflects our species' ultimate optimism, that consciousness itself might transcend the very laws that govern matter and energy, that by understanding the paradox deeply enough, we could somehow negotiate with causality itself, bending it to our will rather than accepting our imprisonment within its linear constraints. Yet in the end, we may discover that the grandfather paradox persists not because the universe truly permits such contradictions, but because it reveals something profound about consciousness itself. That the human mind is fundamentally a time-traveling instrument, forever reaching backward to reinterpret its own origins while simultaneously projecting itself into futures that may never arrive. And in this sense, every civilization is already caught within its own temporal loop, endlessly negotiating with a past it cannot change and a future it cannot guarantee. We construct our religions and mythologies around this same temporal loop, origin stories that explain how we came to be, yet simultaneously shape the civilizations that will eventually tell those very stories, as if consciousness itself demands to participate in its own creation even while. In the late 1990s, astronomers made an observation that fundamentally challenged our understanding of cosmic expansion, discovering through careful measurements of distant supernovae that the universe was not slowing down as gravity would predict, but rather accelerating outward at an ever-increasing rate, as though some invisible force was pushing galaxies apart with growing intensity. This phenomenon, which scientists term dark energy, represents approximately 68% of all matter and energy in the observable universe. Yet we cannot see it, touch it, measure it directly, or even begin to comprehend what it fundamentally is, existing as a complete mystery wrapped in mathematical equations that describe its behavior without explaining its nature. The universe should be contracting under the weight of its own gravity, pulling all matter inward toward eventual collapse, and yet observations consistently show that galaxies are moving away from each other faster and faster, defying every expectation and every law of physics we have carefully constructed over centuries of scientific inquiry. We have named this phenomenon, given it variables in our equations, and incorporated it into our models of cosmic evolution. But the simple truth remains that we are observing something that should not exist according to everything we understand about matter, energy, space, and time. Dark energy violates no direct laws because we have never truly understood what laws it might violate, existing in a category of phenomena that seems to operate according to principles completely foreign to our experience and intuition. Over the decades, physicists have proposed countless explanations ranging from Einstein's cosmological constant representing a property of space itself, to quintessence fields permeating all existence, to the possibility that gravity itself behaves differently on cosmic scales than our current theories predict. And yet none of these explanations have gained universal acceptance or provided genuine insight into the mechanism at work. What makes this cosmic mystery particularly unsettling is that we have grown accustomed to its presence, incorporated it into our textbooks, and normalized the fact that the majority of the universe operates according to principles we cannot fathom, accepting that acceleration as simply part of how reality functions despite it being perhaps the greatest mystery in all of science. Yet perhaps this acceptance itself represents a profound shift in scientific thinking, where we have learned to distinguish between describing how the universe behaves and understanding why it behaves that way, recognizing that the map of reality need not be complete to be useful, and that some of the deepest mysteries may ultimately reshape not just our equations, but our fundamental conception of existence itself. The discovery of dark energy has humbled us in a way that few scientific revelations have, reminding us that the universe continues to operate on scales where our most fundamental assumptions break down, and that progress in understanding may require not just better instruments or clever equations, but an entirely new conceptual framework for thinking about the relationship between space, time, and the forces that govern cosmic evolution. Perhaps the greatest lesson dark energy teaches us is that the universe remains fundamentally stranger than our theories, and that humility before the unknown, rather than certainty in our models, may be the truest foundation upon which genuine scientific progress is ultimately built. Imagine a universe where the vast majority of all matter cannot be seen, detected directly, or interacted with through any conventional means. Yet we know with absolute certainty that it exists because we can measure its gravitational effects on everything around us. Dark matter comprises approximately 85% of all matter in the observable universe, yet it remains completely invisible to every instrument we have ever built, leaving us in the peculiar position of having mapped something we cannot observe, calculated its distribution across billions of galaxies, and confirmed its reality through mathematical models and indirect observations, all while maintaining complete ignorance about what it actually is. Galaxies spin too quickly to remain gravitationally bound by the visible matter alone, and clusters of galaxies move with velocities that should tear them apart, yet they hold together as if anchored by invisible chains of matter that outnumber ordinary atoms by 6 to 1. The psychological mechanism that allows us to accept this paradox operates through the principle of mathematical necessity, wherein we trust equations and predictions over sensory evidence, essentially deciding that mathematical consistency matters more than direct observation. When gravitational models fail to match observations, rather than rejecting the observational data, we populate our equations with hypothetical matter that perfectly explains everything while remaining eternally beyond our perception, transforming a fundamental gap in human knowledge into a standard component of cosmological models. We have normalized this strange acceptance of the undetectable by building elaborate theoretical frameworks that treat dark matter as an ordinary substance, assigning it properties, density profiles, and spatial distributions, conducting experiments designed to detect particles that might compose it, all while remaining suspended in a state of profound uncertainty about whether we are chasing something fundamentally real or whether our understanding of gravity itself requires revolutionary revision. The remarkable aspect of this situation lies not in the mystery itself, but in how completely we have accepted the existence of something that violates the basic principle of empirical science, which demands that reality be observable, measurable, and verifiable through direct means. Yet here we stand, absolutely dependent upon invisible matter for the entire architecture of modern cosmology. This inversion of empirical methodology reveals something profound about human cognition. When faced with an unexplainable gap between theory and reality, we possess an almost unlimited capacity to believe in invisible solutions rather than question our foundational assumptions, suggesting that our confidence in dark matter may ultimately tell us more about the psychology of scientific certainty than it does about the actual composition of the cosmos. Perhaps the most unsettling realization emerges when we consider that dark matter's invisibility may not represent a failure of detection, but rather a fundamental limitation in how we perceive reality itself, that we might be like creatures evolved to sense only visible light, eternally blind to entire dimensions of existence that operate according to rules we have yet to even imagine, let alone comprehend. If the visible universe is merely the surface of a vastly deeper reality, then our entire scientific enterprise may be analogous to a blind civilization, meticulously cataloging the ripples on a pond while remaining forever ignorant of the water itself, the container, and the forces that move beneath the surface. A humbling reminder that the map of human knowledge may bear less resemblance to the territory of actual exi. When astronomers first began measuring the rotational speeds of galaxies in the 1970s, they encountered a phenomenon that fundamentally challenged our understanding of the cosmos and the laws of motion that govern celestial mechanics. According to the well-established principles of Newtonian physics, as you move farther away from the center of a rotating object, the orbital speed should decrease in a predictable manner, much like the way planets in our solar system move more slowly as they orbit at greater distances from the Sun. Yet when scientists observed the outer regions of spiral galaxies, they discovered something that should not exist according to all our theoretical frameworks. The rotational velocity of stars and gas clouds remained remarkably constant at vast distances from the galactic center, refusing to slow down as the distance increased. This observation created what became known as the galaxy rotation problem, a contradiction so profound that it suggested either our understanding of gravity was incomplete, or something invisible and undetectable filled the space around galaxies in quantities far exceeding the visible matter we could observe. The mechanism behind this puzzle lies in the gravitational physics we have inherited from centuries of observation and mathematical refinement, a framework so thoroughly tested and validated that it seemed impossible to question its fundamental assumptions. Stars farther from a galaxy's center should experience weaker gravitational pulls, and therefore they should move more slowly in their orbits, yet the evidence clearly showed otherwise, forcing physicists to hypothesize the existence of dark matter, an invisible substance that comprises approximately 85% of all matter in the universe, despite never being directly detected or understood. What makes this cosmic paradox particularly fascinating is how the scientific community has adapted to this mystery, not by accepting that our laws are wrong, but by inventing an entirely new form of matter that we cannot see, touch, measure, or fully comprehend, essentially filling the gaps in our understanding with something as mysterious as the problem itself. We have normalized living within this profound uncertainty, treating dark matter as established fact in our calculations and simulations, even as it remains one of the deepest unsolved mysteries in physics, reminding us that our most confident assertions about reality might be merely descriptions of our own observational limitations rather than fundamental truths about how the universe actually functions. The irony is particularly sharp when we consider that dark matter was proposed as a solution to make our equations work, yet we have built no experiments that can definitively prove its existence or reveal its true nature, leaving us in the peculiar position of having confidence in something we cannot directly observe or confirm, a situation that would be considered unscientific in almost any other context, yet has become the foundation upon which modern cosmology rests. Perhaps the greatest lesson from the galaxy rotation problem is that science advances not by achieving perfect certainty, but by continuously refining our models in response to observations we cannot ignore, and future generations may look back on dark matter as we now regard phlogiston, a placeholder name for something real whose true nature we finally came to understand through methods we have not yet imagined. Until then, we continue to map the universe using an invisible scaffolding, confident in our mathematics while remaining humbled by the cosmos's refusal to reveal all its secrets at once. Imagine standing at the event horizon of a black hole, that point of no return beyond which nothing, not even light itself, can escape the gravitational pull of a collapsed star. And imagine that you are holding in your hands all the information of the universe compressed into a single quantum state, every particle, every wave function, every probability encoded into something so fundamentally real that destroying it would violate the deepest conservation laws of physics. And now imagine dropping that information past the event horizon into the black hole itself, where according to Stephen Hawking's calculations, the black hole will eventually evaporate through radiation, taking all that information with it into absolute nothingness, and this creates what physicists call the information paradox. A direct contradiction between quantum mechanics, which says information can never truly be destroyed, and general relativity, which says black holes can indeed evaporate and vanish completely. The Firewall paradox emerges from attempts to resolve this contradiction, proposing that the event horizon itself, that seemingly smooth and unremarkable boundary in spacetime that classical physics treats as an ordinary surface, must instead be a region of extraordinarily violent and energetic quantum activity, a literal wall of high-energy particles and radiation that would instantly incinerate anything attempting to cross it. Which creates an even deeper problem because Einstein's equivalence principle, one of the foundational pillars of general relativity, insists that someone freely falling toward a black hole should experience nothing special at the event horizon, should feel no tidal forces or violent energies at the moment of crossing, should pass through as though it were any other region of space. The mechanism underlying this paradox flows from our competing mathematical frameworks, each internally consistent yet mutually contradictory when applied to the same scenario, and the human mind, trained through centuries of scientific progress to expect that nature follows a single coherent set of rules, struggles deeply with the possibility that reality might actually contain fundamental contradictions, or that our best theories might both be partially wrong in ways we have yet to discover. We have normalized this paradox by treating it as an unsolved mathematical puzzle, rather than confronting the possibility that our understanding of the universe at its deepest level might require revolutionary change. And physicists continue publishing papers exploring resolution mechanisms, each adding layers of theoretical complexity without fundamentally resolving whether information truly survives, whether the firewall truly exists, or whether both our greatest theories need complete reformulation to account for the space where black holes and quantum mechanics collide. Perhaps the deepest discomfort lies not in any single failed equation, but in the recognition that we may have reached the limits of what our current mathematical language can express, that the universe at the Planck scale might operate according to principles so fundamentally alien to our intuitions about locality, causality, and information that we lack even the conceptual vocabulary to properly formulate the question, let alone discover its answer. And yet this very inadequacy of language might itself be the crucial insight, that the firewall paradox persists not because nature is fundamentally contradictory, but because we are asking questions formulated in a conceptual framework that cannot accommodate the answer, much as a two-dimensional being might struggle eternally to understand the nature of depth without realizing that the problem lies not in reality, but in the dimensionality of their inquiry. Deep within the mathematical foundations of modern theoretical physics lies a conjecture so profound and unsettling that it challenges our most basic intuitions about the nature of space, time, and connection itself. A hypothesis proposed by Juan Maldacena and Lars Thorlacius suggesting that the Einstein-Rosen bridge, the theoretical wormhole that Einstein himself conceived as a mathematical curiosity, might actually be equivalent to Einstein-Podolsky-Rosen entanglement. The spooky instantaneous correlation between distant quantum particles that troubled even Einstein in his most skeptical moments. This equivalence proposes that what appears to be two seemingly impossible phenomena might actually be two different descriptions of the same underlying reality, that a wormhole connecting two distant regions of spacetime might literally be the geometric manifestation of quantum entanglement, and that particles separated by vast cosmic distances with no classical connection whatsoever could be linked through microscopic, fluctuating tunnels in the fabric of reality itself. The psychological mechanism that keeps this idea alive despite its radical implications is humanity's deep need to unify disparate phenomena under a single explanatory framework, the same impulse that drove physicists to seek a grand unified theory, and that makes us uncomfortable when we discover that nature operates according to two fundamentally incompatible rule sets, one for the very large and one for the very small. Yet here we find ourselves continuing to develop mathematical formalisms around ER equals EPR as though it were established truth rather than speculative conjecture. We have normalized this idea by treating it as a serious research direction in theoretical physics, publishing peer-reviewed papers, inviting experts to conferences, and training graduate students in the mathematical machinery required to explore its implications, all while acknowledging that it remains fundamentally unprovable through any conceivable experiment that our current or even foreseeable technology could perform. And this persistence of an untestable but mathematically elegant idea in the discourse of serious physics suggests something curious about how human knowledge systems actually function when confronted with the limits of empirical verification. Perhaps most strikingly, the very impossibility of empirical verification has become, paradoxically, a feature rather than a bug, a mathematical concept so elegant that it generates its own gravitational pull within the physics community, drawing brilliant minds into its orbit precisely because it promises to dissolve the boundary between geometry and quantum mechanics in ways that feel intuitively correct, even if they remain forever beyond experimental reach. This phenomenon mirrors the historical pattern of how mathematics itself often precedes physical discovery. Non-Euclidean geometry existed as pure abstraction for decades before Einstein found it essential to describing gravity. Yet equals remains uniquely suspended in a liminal space where mathematical beauty has become almost sufficient justification for continued investigation. Even as physicists privately acknowledge that they may be studying the structure of their own equations rather than the structure of reality itself. And yet this ambiguity, whether we are discovering nature or merely admiring the internal consistency of our mathematical frameworks, may itself be the wrong question to ask, for it assumes a sharp boundary between map and territory that quantum mechanics has already taught us may not exist, suggesting that perhaps the deepest insights emerge precisely at those moments when physicists can no longer distinguish between what is true about the universe and what is true ob. Imagine that everything you perceive, every object you touch, every color you see, and every sound you hear might not actually exist in the way your mind assumes it does, but rather represents a projection or encoding of information from a lower dimensional surface somewhere beyond your perception, a concept that emerges from the intersection of quantum mechanics, black hole thermodynamics, and string theory, where physicists have discovered that the information contained within a three-dimensional volume of space can theoretically be completely described by information encoded on its two-dimensional boundary. Much like how a three-dimensional hologram can be generated from a two-dimensional surface containing specific patterns of light and shadow, suggesting that our entire universe might function as an elaborate holographic projection where what we experience is solid. Three-dimensional reality is actually the manifestation of mathematical information existing on some distant, lower-dimensional cosmic boundary that we cannot directly access or perceive. The mechanism behind this paradigm-shifting concept originates in the work of physicist Juan Maldacena, who proposed that a gravitational theory in a higher dimensional space might be equivalent to a quantum field theory on its lower dimensional boundary, creating a mathematical correspondence so precise and elegant that it suggests our experience of three-dimensional space with gravity might be fundamentally equivalent to a two-dimensional quantum system without gravity, implying that depth itself. That quality of space extending away from us in all directions might be an emergent property rather than a fundamental feature of reality. And this realization emerges not from mysticism, but from rigorous mathematical analysis, attempting to reconcile the contradictions between quantum mechanics and general relativity. Yet despite the profound implications of this theory, despite the fact that if true it would mean that the dimension we experience as primary and fundamental might actually be derivative and secondary, despite the revolutionary nature of this concept that challenges our most basic assumptions about the nature of existence itself, humanity continues to navigate daily life with absolute certainty in the three-dimensionality of space. Treating depth and distance as obviously real rather than potentially emergent phenomena, building structures and planning futures based on spatial assumptions that might ultimately be illusions projected from information encoded on surfaces we cannot see. And we have normalized this cognitive dissonance so thoroughly that the holographic principle remains confined largely to theoretical physics discussions rather than reshaping how we fundamentally understand our place in the cosmos. Perhaps the most unsettling aspect of the holographic principle is that we possess no mechanism to detect or verify whether we ourselves exist within such a projection, meaning that if reality is indeed holographic, the very consciousness questioning this possibility might itself be nothing more than an intricate pattern of information encoded on a boundary we will never access, forever trapped within our own projection, unable to step outside the hologram to observe its source. This paradox mirrors ancient philosophical thought experiments like Plato's cave, where prisoners perceive only shadows on a wall and mistake them for reality, suggesting that humanity has long intuited the possibility of living within layers of illusion, and the holographic principle might represent our modern mathematical language for expressing this timeless uncertainty about the fundamental nature of perception and existence. Imagine standing at the edge of the universe itself, armed with equations and observations, only to discover that the most fundamental force governing all existence appears to be one of the most embarrassingly wrong predictions in the history of science. The cosmological constant catastrophe represents one of the deepest unsolved mysteries in theoretical physics, a problem so severe that it challenges our entire understanding of reality at the most fundamental level. When physicists calculate what the vacuum energy of space should be, accounting for all the quantum fields that permeate existence, their mathematics produces a number that is so incomprehensibly large, so staggeringly massive compared to what we observe in the universe, that the discrepancy is often described as the worst prediction in the history of science. The observed acceleration of the universe expansion suggests that dark energy has a density corresponding to a cosmological constant. Yet when physicists attempt to calculate this value from first principles using quantum field theory, they arrive at a prediction that is off by a factor of somewhere between 10 to the power of 120, a number so vast that human language struggles to even conceptualize the magnitude of the error. What makes this catastrophe particularly haunting is that we have no theoretical framework that adequately explains this absurd disparity, no mechanism that naturally produces the incredibly small but non-zero cosmological constant we observe. The psychological mechanism behind our continued work despite this paradox stems from the fact that we have normalized one of the most inexplicable failures in predictive science, treating it as simply another unsolved problem rather than confronting the possibility that our entire theoretical foundation might be fundamentally flawed in ways we cannot yet perceive. We continue building upon quantum field theory and general relativity, incrementally refining our models and proposing exotic explanations involving extra dimensions, modified gravity, or vacuum energy dynamics, because the alternative, that these pillars of modern physics might be incomplete or incorrect at their core, feels almost too destabilizing to contemplate. The cosmological constant catastrophe persists in our scientific consciousness as this strange, unresolved tension, a reminder that despite centuries of progress and remarkable technological achievements, we are still fundamentally ignorant about the nature of the universe we inhabit, and we have learned to live with this uncertainty by compartmentalizing it, by acknowledging it in academic papers while continuing to build our theories upon the very foundations it calls into question. Perhaps the deepest irony is that dark energy, whatever it fundamentally is, now comprises nearly 70% of the universe's total energy density, meaning that the very phenomenon we cannot explain dominates the cosmos more completely than all the ordinary matter and energy we have spent centuries learning to understand. In this sense, the cosmological constant catastrophe is not merely an embarrassing footnote to our scientific achievements. It is a humbling revelation that the universe's primary constituent remains profoundly mysterious, stubbornly resistant to the theoretical frameworks we have constructed with such pride and precision. Yet this very mystery may ultimately prove to be our greatest gift, for it suggests that beyond the elegant mathematics we have mastered lies a deeper layer of reality waiting to be discovered, a truth that will force us to expand our conception of what physics can be and what the universe truly is at its most fundamental level. Consider the most fundamental observation in modern physics. Empty space is not actually empty at all, but rather seethes with quantum fluctuations that create and destroy virtual particles in intervals so brief that the uncertainty principle permits their existence without violating conservation laws. And yet when physicists attempt to calculate the total energy density of this vacuum, they arrive at a number so catastrophically large that it should curve spacetime into an infinitely dense singularity, crushing the entire universe into oblivion in an instant, and yet we observe a cosmos that expands at a relatively gentle rate with a universe that remains relatively flat and stable, suggesting that the actual vacuum energy is either zero or incomprehensibly smaller than theoretical predictions, a discrepancy known as the cosmological constant problem. The psychological mechanism underlying our acceptance of this paradox stems from our ability to compartmentalize different theoretical frameworks into separate domains of understanding, treating quantum mechanics as valid in its domain and general relativity as valid in its own, without forcing them to genuinely reconcile their predictions about the vacuum itself. We have become accustomed to the idea that reality operates according to rules we have not yet unified, and this unresolved tension has paradoxically become normalized in the scientific community as simply another mystery awaiting future theoretical breakthroughs rather than as evidence of fundamental error in our approach. The vacuum energy problem persists not because we lack experimental data or observational evidence, but because the mathematics that describes the quantum world and the mathematics that describes gravity refuse to speak the same language about the nature of nothingness itself. And we have learned to live with this contradiction by acknowledging it openly in academic literature while continuing with practical research that operates around it rather than through it, creating an intellectual landscape where one of the largest known discrepancies between theory and observation has become almost invisible through sheer habituation and professional acceptance. This normalization is perhaps most evident in how cosmologists casually invoke dark energy as a solution while remaining fundamentally uncertain whether they are describing a genuine physical phenomenon or merely parametrizing their ignorance, much as ancient astronomers once added epicycles to preserve a geocentric model rather than questioning the model itself. The vacuum energy problem thus stands as a monument to the limits of human intuition. We can build machines that harness quantum mechanics and telescopes that map the cosmic microwave background, yet we cannot reconcile what these technologies reveal about the deepest level of reality without resorting to a kind of comfortable agnosticism about the very foundations upon which both rest. Perhaps most troubling is that this comfortable agnosticism may itself be masking a deeper problem, that we have constructed our theories in such a way that they are fundamentally untestable at the scales where vacuum energy dominates, leaving us with sophisticated mathematical frameworks that can predict almost anything while explaining almost nothing about why the universe exists in the particular configuration we observe rather than collapsing or expanding infinitely. We have, in essence, built an intellectual fortress around our ignorance and called it science. Yet the most humbling aspect of this fortress is that it continues to generate predictions of extraordinary precision in domains where it applies, suggesting that our ignorance may be not of reality itself, but of how to properly ask reality the questions we. Imagine standing at the edge of the observable universe, looking back at the moment of the Big Bang itself, and you encounter a puzzle so profound that it challenges our understanding of how the cosmos could possibly exist in its current form. The horizon problem emerges from a deeply unsettling observation about the early universe, one that suggests regions of space that could never have communicated with one another somehow ended up with nearly identical physical properties, a uniformity so precise that it defies conventional explanation. In the first fraction of a second after the Big Bang, the universe expanded so rapidly that light traveling from one region could never have reached another region before inflation separated them permanently. Yet when astronomers peer through telescopes and examine the cosmic microwave background radiation that permeates all of space, they find that distant patches of the universe, regions so far apart that they could never have exchanged heat or information, possess temperatures that match to within 1 part in 100,000. This extraordinary synchronization exists without any apparent mechanism to account for it, without any known way for these causally disconnected regions to have somehow coordinated their properties or reached thermal equilibrium. The logical mechanism underlying our confusion stems from the fact that in our everyday experience, uniformity and equilibrium require communication and interaction, processes that demand time and the ability for signals to travel between objects. Yet the universe appears to have achieved perfect uniformity before any such communication could have occurred across cosmic distances. We have normalized this impossibility through the framework of cosmic inflation theory, the hypothesis that the universe underwent an exponentially rapid expansion in its earliest moments, a process so violent and swift that it could have taken a small, causally connected region and stretched it to encompass the entire observable universe we see today, thereby explaining why everything appears so uniform despite its apparent inability to have done so. Yet even this elegant solution introduces its own mysteries and paradoxes that remain fundamentally unresolved in modern physics. Among the deepest of these unresolved questions lies the nature of inflation itself. What caused it to begin, what governed its duration, and whether the mechanism that solved the horizon problem might have inadvertently created countless other universes beyond our ability to observe or measure, each potentially governed by entirely different physical laws than our own. If inflation did indeed spawn a vast multiverse of disconnected universes, then the horizon problem transforms from a puzzle about our cosmos into a question about why we find ourselves in a universe where the conditions for life and consciousness could emerge at all. A transformation that pushes the horizon problem from the realm of pure physics into the philosophical territory of cosmic coincidence and selection. This anthropic perspective, that we observe a universe fine-tuned for our existence precisely, because we could not exist to observe any other kind, suggests that the horizon problem may ultimately be unanswerable through physics alone, requiring us to grapple with questions about observation, selection, and the nature of cosmic possibility itself. Yet perhaps this is the horizon problem's deepest lesson. that some questions about the cosmos may ultimately reflect the limits of our current theoretical frameworks rather than genuine mysteries of nature, inviting us to consider whether future physicists might dissolve this apparent paradox through entirely new ways of understanding space, time, and causality itself. Imagine the universe as a vast canvas stretching infinitely in all directions, and then consider that physicists have discovered something profoundly unsettling about its shape and curvature. The flatness problem emerges from one of cosmology's most puzzling observations. Our universe appears to be geometrically flat, meaning that the geometry of spacetime follows Euclidean principles where parallel lines remain parallel and the angles of a triangle sum to exactly 180 degrees. This flatness seems almost impossibly precise, as if someone had carefully fine-tuned the density of matter and energy in the cosmos to an extraordinary degree of accuracy. The problem lies not in the observation itself, but in the fact that any deviation from this precise flatness would have compounded exponentially throughout cosmic history, resulting in a universe that would be wildly curved and nothing like what we observe today. In the early moments after the Big Bang, the density of the universe would have needed to match the critical density with an accuracy of 1 part in 10 to the 60th power, a precision so exacting that it defies intuitive comprehension and seems to demand explanation rather than mere acceptance. The psychological mechanism at work here involves our struggle to reconcile apparent design with the laws of probability in physics. When we encounter something that appears deliberately calibrated, our minds instinctively search for either a designer or a mechanism that produced such precision, because randomness alone seems incapable of generating such fine-tuned conditions. This creates a cognitive tension between what we observe and what our understanding of chance and causality suggests should occur, leading us to question whether the universe truly is flat or whether we are missing some deeper principle that would make flatness inevitable rather than improbable. The mechanism also involves our tendency to normalize extraordinary coincidences once they are established as fact, accepting the universe's flatness as simply how things are rather than continually marveling at how unlikely such a condition should be. Despite possessing no logical mechanism that adequately explains why the universe should be flat, we have integrated this observation into our standard model of cosmology and moved forward with our investigations. The most common resolution involves inflation theory, which proposes that the early universe expanded so rapidly that any initial curvature was stretched to imperceptible levels, much as inflating a balloon makes its surface appear increasingly flat to an observer standing upon it. Yet this theory itself requires explanations and creates new mysteries about what drove inflation and why the inflationary field possessed the properties it did. We have somehow normalized this profound puzzle, discussing it in academic papers and textbooks, as though it were merely another interesting feature of cosmology, rather than a genuine paradox that challenges our understanding of why the universe exists in a state that seems specifically arranged to permit complex structures and conscious observers to arise within it. This tendency to move past profound mysteries reflects perhaps the deepest cognitive bias of all: our capacity to transform the inexplicable into the merely technical, converting questions about existence itself into problems awaiting the next theoretical innovation, until we forget we were ever puzzled at all. And in this process of normalization, we forget that the flatness problem remains fundamentally unresolved. We have merely found a plausible mechanism that shifts the mystery backward in time rather than eliminating it, trading one puzzle for another, while the deeper question of why initial conditions. In the beginning of our universe, during those first fractions of a second after the Big Bang, something extraordinary and deeply troubling occurred that physicists still struggle to explain. The fundamental laws of physics, as we understand them, predict that matter and antimatter should have been created in perfectly equal quantities, like two sides of a cosmic equation balancing themselves out. For every particle of matter composed of baryons, there should have been an identical antibaryon waiting to annihilate it in a flash of pure energy. According to the equations that govern particle physics, these two forms should have emerged symmetrically from the quantum foam of creation, and within moments they should have collided and destroyed each other completely, leaving behind only radiation and energy in an empty, lifeless universe. Yet somehow, inexplicably, this did not happen. Instead, there existed a tiny, incomprehensible asymmetry in the early universe, perhaps only one extra particle of matter for every billion particles of matter-antimatter pairs that annihilated each other. This minuscule imbalance, this almost negligible preference for matter over antimatter, was enough to leave behind a residue of particles that would eventually cool, condense, and form the galaxies, stars, planets, and ultimately all the complexity of existence that we observe today. Our very existence depends on this asymmetry, this fundamental broken symmetry that should not have occurred according to our best theoretical models. Physicists have proposed numerous mechanisms to explain how this bias could have arisen, from differences in how matter and antimatter particles decay, to hypothetical processes that violated conservation laws in the earliest moments of time. Yet none of these explanations fully resolves the mystery or provides complete mathematical satisfaction. We live in a universe that should not exist, that defies the elegant symmetry of our equations, and we continue to accept this paradox as simply another unsolved problem in physics, another mystery filed away while we focus our attention on other questions. Perhaps the deepest irony is that this very asymmetry, this cosmic imperfection, may be the only reason we exist at all to ponder the question of why it occurred, making baryon asymmetry not just a physics problem, but a prerequisite for consciousness itself. And yet this circular dependency, where our existence hinges on solving a mystery that may only be answerable through our own conscious investigation, suggests that baryon asymmetry represents not merely a gap in our understanding, but perhaps a fundamental limit to what physics alone can ultimately explain about why there is something rather than nothing. Some physicists speculate that the answer may lie beyond our current framework entirely, perhaps in extra dimensions, quantum gravity effects, or even in the structure of time itself, while others wonder whether the asymmetry represents a selection effect, where universes without this imbalance simply could never develop observers to question their absence. In this view, we would be not discoverers of baryon asymmetry's origin, but inevitable products of it, conscious observers shaped by the very imbalance we seek to understand, forever separated from the initial conditions that made us possible by an unbridgeable gulf of time and thermodynamic irreversibility. This perspective transforms baryon asymmetry from a mere technical puzzle into a profound statement about the nature of existence itself, a reminder that the most fundamental questions about reality may ultimately require us to grapple not just with the mathematics of particle physics, but with the philosophical implications of being observers embedded within the very cosmos we seek to. When the universe began in that first incomprehensible moment of the Big Bang, the laws of physics dictated that matter and antimatter should have been created in perfectly equal quantities, two sides of the same cosmic coin existing in pristine symmetry. For every electron, there should have been a positron, for every proton, an antiproton, and when these fundamental particles encountered one another, they would annihilate in brilliant flashes of pure energy, converting their mass entirely into radiation, according to Einstein's elegant equation. Yet here we stand, in a universe dominated overwhelmingly by ordinary matter, surrounded by galaxies and stars and planets composed entirely of the stuff we call normal, while antimatter has vanished almost completely from the observable cosmos, leaving behind only the faintest traces detectable in our most sensitive laboratory experiments. The asymmetry is staggering and profound. For every billion antiparticles that might have survived the violent early universe, there exists 1 billion and 1 particles of matter, a difference so minute yet so catastrophically consequential that it represents perhaps the deepest mystery in all of physics, a fundamental imbalance that should not exist yet demonstrably does. Scientists have constructed elaborate theories to explain this absence, proposing exotic processes that might have slightly favored matter over antimatter during those first fractions of a second after creation, mechanisms involving what they call charge parity violation, where certain fundamental forces behave differently depending on whether you reverse the direction of time or flip the signs of electrical charges. Yet none of these explanations possess the clarity and inevitability that would make them feel like genuine solutions. The mystery persists in our understanding like an unsolved riddle whispered at the foundation of reality itself, a question so fundamental that answering it might require us to reconsider everything we think we know about how the universe actually works. We have somehow become accustomed to this profound asymmetry, accepting it as simply how things are rather than as a screaming contradiction that demands resolution, incorporating this missing antimatter into our models and equations as if its absence were merely another parameter to be measured rather than a void that should not exist at all. Yet perhaps this acceptance itself reveals something profound, that the universe we inhabit, improbable as it is, exists precisely because of this imbalance, because the tiniest preference for matter over antimatter in those first moments allowed structure and complexity to emerge from the primordial fire, meaning that we ourselves are products of this cosmic asymmetry, witnesses to and beneficiaries of the very mystery we struggle to understand. In this sense, the missing antimatter is not merely a puzzle to be solved, but a prerequisite for our existence. Without that infinitesimal cosmic bias, the universe would have annihilated itself completely into pure light, leaving no stage upon which stars could ignite, life could emerge, or consciousness could contemplate its own origins. We are quite literally children of imbalance, our atoms forged in stellar furnaces that could only exist because matter slightly outnumbered its shadowy twin in the moments when the universe was born. Every atom in our bodies, every carbon nucleus fueling our cells, every iron atom carrying oxygen through our blood, represents a triumph of matter over its antimatter counterpart, a victory so ancient and so complete that we have inherited a universe where antimatter exists only as a fleeting ghost in particle accelerators, a phantom we must laboriously create rather than find. The universe is incomprehensibly vast, containing an estimated 2 trillion galaxies, each with hundreds of billions of stars, and the statistical probability that Earth is the only planet harboring intelligent life seems almost negligibly small when we consider the sheer scale of cosmic real, a state available for the emergence of consciousness and civilization. Yet when we look up at the night sky and listen intently to the cosmic void through our most sensitive radio telescopes and astronomical equipment, we encounter nothing but silence, an absolute and deafening absence of signals or evidence that any other intelligent species has ever emerged, survived, or attempted to communicate across the distances between worlds. This contradiction, first articulated by physicist Enrico Fermi in the mid-20th century through his famous question of where everybody is, creates a profound intellectual tension that has haunted scientific consciousness for decades. The mechanism behind this paradox operates on the foundation of probability and expectation. If the universe is truly so immense and ancient, with billions of years of time for life to develop and evolve toward intelligence and technological sophistication, then surely by now we should have detected unmistakable signs of extraterrestrial civilizations, whether through intentional messages, waste radiation from their technologies, or physical artifacts sent across the stars. We have developed mathematical models like the Drake equation that attempt to estimate the number of communicative civilizations in our galaxy alone, and these calculations often yield numbers in the thousands or millions, yet our experience remains one of profound solitude and cosmic isolation. What makes this paradox particularly unsettling is not merely the absence of evidence, but rather our collective normalization of this absence despite its logical impossibility, as though silence itself has become an acceptable answer to a question that demands explanation. We continue our lives and our scientific pursuits while simultaneously acknowledging that the universe should be teeming with neighbors, and yet we treat that silence as an ordinary condition rather than a revelation that something fundamental about our assumptions regarding probability, the longevity of civilizations, the nature of intelligence, or the universe itself must be profoundly wrong in ways we have yet to comprehend or articulate. Perhaps the silence itself is the universe's most eloquent answer, suggesting that the great filter, some insurmountable barrier that prevents civilizations from reaching our stage of development or surviving long enough to communicate, lies either behind us in our evolutionary past or ahead of us in a future we have yet to face, making our survival and flourishing far more improbable than our initial calculations ever suggested. If the great filter lies ahead of us, then every civilization that reaches our current technological threshold faces the same existential crucible, a narrow passage through which few, if any, successfully navigate, suggesting that the universe may be populated not with thriving galactic societies, but with the silent graves of countless species that solved the riddle of the atom only to perish by its power, or achieve the technological means to destroy themselves faster than they could unite as a species to ensure their survival. This sobering possibility transforms the Fermi paradox from a mere astronomical curiosity into a mirror reflecting our own precarious moment in history, where the same technologies that enabled our ascendance, nuclear power, artificial intelligence, synthetic biology, now present existential risks that may ultimately determine whether humanity becomes another silent footnote in the. Imagine stepping outside on a clear night and gazing up at the vast expanse above you, observing the darkness that stretches infinitely between the scattered points of light we call stars, and then consider this deeply troubling question. If the universe is infinite in all directions and filled with an infinite number of stars distributed throughout space, why is the night sky not blazingly bright? If you look in any direction, your line of sight should eventually reach a star somewhere out there in that infinite cosmos. And if that is true, then logically every single point in the night sky should be illuminated by starlight, turning darkness into brilliance. This is the essential paradox that troubled the mind of Heinrich Olbers in 1826. Though the puzzle had been pondered by earlier thinkers, including Thomas Digges and others who recognized this fundamental inconsistency between our observations and our theoretical understanding of an infinite universe. The psychological mechanism at work here involves our deep intuition about how light and geometry should function, combined with our assumptions about the structure of the cosmos itself. When we assume an infinite universe with infinite stars, the mathematics inexorably leads us to the conclusion that the entire night sky must glow with the combined light of all those distant suns, yet our eyes tell us this is not the case. We experience a profound dissonance between what should be true according to logic and what we actually observe in reality. Throughout history, various explanations have been proposed to resolve this contradiction, from the notion that dust clouds obscure distant starlight to the revolutionary idea that the universe is not eternal but had a beginning, to the modern understanding that the universe is expanding and therefore the light from infinitely distant galaxies never reaches us. Yet despite the fact that physicists and cosmologists have developed sophisticated explanations for this paradox, it persists in our collective consciousness as a troubling reminder of how our intuitions about space, infinity, and light can lead us astray, demonstrating that the universe continues to harbor mysteries that challenge our most fundamental assumptions about existence itself. The paradox ultimately reveals how cosmological questions cannot be answered by intuition alone, but require us to peer deeper into the nature of time, space, and the finite age of the observable universe itself, reminding us that what we see in the darkness above is not the absence of stars, but rather the presence of cosmic history unfolding across billions of years of light travel time. When we finally detect the faint glow of the cosmic microwave background, the ancient light from the universe's infancy, we glimpse the very boundary of our observable cosmos, a tangible reminder that the darkness of the night sky is not emptiness but a window into time itself, where the oldest light has traveled so far that its energy has been redshifted into invisibility. And in this way, Olbers' paradox transforms from a mere intellectual puzzle into a profound meditation on the limits of human perception, a reminder that the universe's true nature often lies hidden not in what we can see, but in what the darkness itself reveals about time, distance, and the finite span of cosmic visibility that defines our place within an ancient and expanding cosmos. The darkness we observe is therefore not a flaw in our understanding but a feature, a cosmic clock that measures the distance to ancient events and reminds us that we inhabit a universe young enough that its light has not yet filled every corner of space, a humbling realization that transforms a simple question about brightness into a profound insight about our owl. Imagine standing in a vast library where two equally reliable librarians have measured the same shelf and arrived at measurements that cannot both be true, yet both librarians have checked their tools repeatedly and found no fault in their instruments or methodology. This is the essence of the Hubble tension, one of the most perplexing anomalies in modern cosmology that sits at the very heart of how we understand the universe's expansion. The Hubble constant represents the rate at which the universe is expanding at this very moment, and it should be a single, definite number that we can measure and verify. However, when astronomers measure this expansion rate using one method based on nearby stars and supernovae distances, they arrive at approximately 73 kilometers per second per megaparsec, while measurements derived from observations of the cosmic microwave background radiation, the ancient light left over from the Big Bang itself, consistently yield values around 67 kilometers per second per megaparsec. This discrepancy of roughly 6 kilometers per second per megaparsec might sound insignificant to the untrained ear, but in the precise language of physics, this gap represents something far more troubling than a simple measurement error or instrumental miscalibration. The first measurement method uses what astronomers call the cosmic distance ladder, where they establish the distances to nearby stars using parallax measurements, then use these calibrated distances to measure supernovae brightness and determine how far away distant galaxies truly are. The second method employs the patterns and ripples visible in the oldest light in the universe to mathematically work backward and predict what the current expansion rate ought to be, assuming our current understanding of the universe's composition and history is correct. Both methods are independently verified by multiple teams of researchers using different instruments and refined techniques, and yet they persistently refuse to converge. What makes this tension so profoundly disturbing to physicists is that if one measurement is correct, then our understanding of either the universe's distance scale or its fundamental composition and evolution must be fundamentally wrong in ways we have not yet discovered. The psychological mechanism driving the continued acceptance of this paradox is that science has developed a remarkable capacity to house contradictions within specialized domains, allowing different teams to continue their work without forcing an immediate confrontation with the problem. Physicists working on the cosmic distance ladder do not necessarily need to resolve the tension with cosmic microwave background measurements in order to publish their findings and advance their research, and the same applies inversely, creating what might be called compartmentalized acceptance. We have normalized this contradiction by treating it as a temporary puzzle awaiting future technology or theoretical insights, rather than as evidence that something fundamental must give way. And in doing so, we persist in a state of productive uncertainty that somehow coexists with our unwavering confidence in our cosmic measurements and models. Yet this productive uncertainty carries an implicit wager that the universe, in its fundamental nature, remains comprehensible to us, that the fault lies in our instruments or methods rather than in our assumptions about reality itself, and that patience combined with better measurements will eventually reveal which librarian was right all along. But what if both librarians are right, and the universe itself has changed its expansion rate in ways our current models cannot accommodate? A possibility that would require us to fundamentally reimagine, not Merrill. In the 1970s, NASA launched two spacecraft called Pioneer 10 and Pioneer 11 into the depths of space, sending them on trajectories that would carry them beyond the orbits of the outer planets and eventually out of our solar system entirely. These remarkable machines were equipped with instruments to study the cosmic environment, radioisotope thermoelectric generators to power their systems, and communication equipment to send signals back across the vast distances separating them from Earth. As these spacecraft journeyed outward year after year, scientists on Earth tracked their positions with extraordinary precision, measuring the subtle variations in the frequency of their radio signals using the Doppler effect, the same principle that makes an ambulance siren change pitch as it moves away from you. What they discovered was deeply puzzling. The Pioneer spacecraft were slowing down more than they should have been based on all known gravitational influences and solar radiation pressure that physicists could calculate. The deceleration was tiny, only a few millimeters per second per year, but it was consistent, measurable, and utterly inexplicable within the framework of established physics. Engineers and scientists proposed numerous explanations for this phenomenon, examining every conceivable source of unexpected force that might be acting upon the craft. They considered uneven heat radiation from the spacecraft's power sources, solar-wind interactions, collisions with dust particles, subtle variations in gravitational fields, and even the possibility that our understanding of gravity itself might require modification at such vast scales. The anomaly persisted through decades of investigation, resisting easy categorization and refusing to surrender to conventional explanations. Despite its minuscule magnitude and the fact that it ultimately did not prevent the spacecraft from achieving their mission objectives, the Pioneer anomaly became a symbol of the universe's capacity to surprise us, a reminder that even in our most carefully measured observations, mysteries can hide within the data. It represents that peculiar frontier where measurement becomes so precise that the unknown begins to whisper through the gaps in our understanding, and we are forced to confront the possibility that something fundamental about our physical laws might still elude our grasp. Yet this humility proved warranted. In 2012, researchers analyzing decades of thermal data finally resolved the mystery, discovering that heat radiating asymmetrically from the spacecraft's instruments could account for nearly all the anomalous acceleration. A solution that vindicated physics while reminding us that sometimes the universe's secrets yield not to revolutionary new theories, but to more careful examination of what we thought we already understood. The pioneer anomaly thus stands as a cautionary tale for modern science, that exotic explanations, while intellectually seductive, sometimes obscure simpler truths lurking in the details we have overlooked, and that the greatest discoveries often emerge not from bold theoretical leaps, but from the unglamorous work of rigorous data analysis and meticulous attention to the mundane mechanics of our instruments. This lesson resonates throughout modern science, from the discovery that certain astronomical observations attributed to dark matter might instead reflect subtle instrumental biases, to the recognition that some anomalies in particle physics experiments vanish under more rigorous accounting of experimental apparatus. A humbling reminder that the universe often teaches us more about our own limitations than about its fundamental nature. Imagine a spacecraft traveling through the vast emptiness of space, approaching Earth at a carefully calculated velocity, its trajectory mapped by our most precise mathematical models and gravitational predictions. And yet when it passes by our planet, something unexpected happens to its speed that we cannot fully explain. This is the flyby anomaly, a phenomenon where spacecraft performing gravity-assist maneuvers around Earth experience an unexplained change in velocity, either gaining or losing speed in ways that our current understanding of physics suggests should not occur at all. The anomaly was first noticed with the Galileo spacecraft in the 1990s, and since then, multiple spacecraft including NEAR Shoemaker, Cassini, and Rosetta have exhibited similar velocity changes during their Earth flybys, creating a persistent mystery that challenges our foundational understanding of gravity and orbital mechanics. The velocities involved are remarkably small, typically changes of mere millimeters per second, yet they are consistently measurable and reproducible, suggesting this is not random measurement error, but something genuinely occurring in the physics of these encounters. Scientists have examined countless conventional explanations, including relativistic effects, atmospheric drag at extremely high altitudes, radiation pressure from the sun, and gravitational influences from the moon and sun. And yet none of these mechanisms can fully account for the observed anomalies in every case. The psychological mechanism here involves our deep confidence in Newtonian and Einsteinian mechanics, theories that have been tested across centuries and have proven extraordinarily accurate in nearly every other scenario, creating a cognitive dissonance when we encounter these small but persistent deviations that resist explanation. We have normalized this paradox by continuing to add small correction factors to our calculations, by suggesting that there may be unknown physics at work, by acknowledging that the anomaly remains unsolved rather than fundamentally challenging our worldview, and by treating it as an interesting footnote rather than a red flag that something deeper might be wrong with our understanding of how gravity truly operates on small scales or at specific velocity ranges. The flyby anomaly persists in a strange state of acceptance, acknowledged by the scientific community, yet not commanding the urgent investigative resources it might deserve, perhaps because the effect is so small that it does not threaten practical space missions, even as it hints that our comprehension of the universe's fundamental rules remains incomplete in ways we have not yet discovered. Yet this very complacency may be the cost of our comfort. By accepting small anomalies as mere measurement quirks rather than investigating them rigorously, we risk overlooking the subtle cracks in our theoretical foundation that might, if examined closely enough, lead us toward a more complete and truthful understanding of how gravity actually behaves in the universe. Consider that history is littered with such dismissed anomalies. The precession of Mercury's orbit seemed trivial until it revealed the need for Einstein's relativity, and we might ask ourselves whether the flyby anomaly represents a similar doorway, one we are simply not yet curious enough or brave enough to walk through. The question becomes whether we possess the intellectual humility to recognize that our most successful theories might have hidden boundaries, limits beyond which they fail in subtle but measurable ways, and whether we are willing to invest in understanding anomalies not because they immediately threaten our technology, but because they whisper of truths we have not yet learned to hear. Consider the moment when you think of someone you haven't spoken to in years, and within minutes they call you, or you receive a message from them entirely unprompted, a phenomenon so striking that it seems to defy the randomness of probability itself. Or imagine the uncanny experience of noticing a particular word or concept repeatedly throughout your day, appearing in conversations, books, advertisements, and overheard dialogue, each occurrence feeling impossibly connected despite the statistical likelihood that such clustering happens constantly in a universe of infinite information. These moments, which we call cosmic coincidences, occupy a peculiar space in human consciousness, existing at the boundary between genuine improbability and the mathematical inevitability that must underpin any sufficiently large system. The mechanism at work here operates through a combination of selective attention and probability compression, where our brains have evolved to recognize patterns as a survival mechanism, causing us to disproportionately notice connections that align with our recent thoughts, while simultaneously filtering out the vastly greater number of non-coincidences that occur every single day. When you think of a friend and they contact you, that singular moment of alignment becomes crystallized in memory, while the hundreds of times you thought of them and nothing happened dissolve into the background of forgotten moments, creating an illusion of connection that feels cosmically orchestrated rather than mathematically inevitable. We have normalized this experience so thoroughly that we have developed an entire vocabulary around it, speaking of synchronicity, destiny, and fate as though these were observable forces rather than artifacts of human perception operating within the constraints of probability. The universe contains enough potential coincidences that some must inevitably occur simply by chance, yet we treat each meaningful feeling connection as evidence of deeper order, perpetually reinforcing a narrative that the cosmos conspires in our favor despite having no mechanism by which this could actually function. Yet this cognitive bias serves a profound psychological purpose. It allows us to construct meaning in an indifferent universe, to feel agency and connection in a cosmos governed by impersonal laws, transforming the cold arithmetic of probability into a narrative where we matter, where invisible threads bind us to others, and where the random becomes redemptive. Perhaps this is why we resist the purely probabilistic explanation even when we understand it intellectually. Because a universe of pure chance feels fundamentally lonely, and the comforting fiction of cosmic connection, however mathematically illusory, allows us to believe that loneliness itself is just another improbable coincidence we haven't yet recognized. And so we find ourselves choosing the narrative that sustains us, consciously aware that our perception of cosmic connection is a beautiful delusion, yet unable, and perhaps unwilling, to abandon it, because the alternative is to accept that meaning is something we must create entirely alone, without the comfort of believing the universe is listening. In this sense, the cosmic coincidence is less a feature of reality and more a feature of consciousness itself, a mirror in which we see reflected back not the universe's design, but our own desperate, beautiful need to believe we are never truly separate from the things we love, even when distance and time suggest otherwise. Perhaps this is why we photograph coincidences, share them in messages, and return to them in conversation, not merely to marvel at improbability, but to collectively affirm that our inner lives are somehow legible to the universe, that conscious. Imagine looking back at the early history of our solar system, approximately 4.5 billion years ago, when our sun was still in its infancy, burning with noticeably less intensity than it does today. According to our understanding of stellar physics and the fundamental processes of nuclear fusion that power stars, the young sun should have been roughly 30% dimmer than it is in our current era, radiating significantly less heat and light into the vast emptiness of space surrounding the newly formed planets. This creates an immediate and troubling paradox that has puzzled scientists for decades, because evidence from ancient geological records and the study of fossilized organisms suggests that liquid water existed abundantly on Earth's surface during this period, with thriving ecosystems and conditions suitable for complex life to emerge and flourish. The mathematics of planetary energy balance tells us this should have been impossible. With a sun 30% fainter, Earth should have been locked in a perpetual ice age, its oceans frozen solid, its surface barren and lifeless, inhospitable to any chemistry that could support biological processes. Yet the fossil record insists otherwise, whispering stories of warm oceans and green landscapes from an age when the sun should have cast only a feeble glow across our young world. Scientists have proposed various mechanisms to explain this paradox, suggesting that greenhouse gases in Earth's ancient atmosphere, particularly methane and carbon dioxide at much higher concentrations than today, may have trapped sufficient solar radiation to maintain temperate conditions despite the sun's faintness. Other theories propose that the young Earth received additional heat from internal processes, from a heavier bombardment of meteorites, or from entirely different configurations of the planet's reflective properties and atmospheric composition that we can scarcely reconstruct with certainty. What makes this paradox particularly unsettling is how it reveals the contingency of our existence, how precarious the conditions were that allowed life to begin, and how many assumptions we must make about the early history of our world. We have normalized this explanatory uncertainty, accepting that somewhere in the interplay of atmospheric chemistry, planetary dynamics, and stellar evolution lies an answer that satisfies both the laws of physics and the unmistakable evidence of ancient life. The faint young sun thus becomes a meditation on the mysteries that persist at the intersection of what we can measure and what we can only infer from distant echoes of the past. Yet perhaps this very uncertainty is itself instructive, reminding us that the story of Earth's habitability has always been one of delicate balance and adaptive transformation, where the conditions necessary for life's persistence required not a single explanation, but an evolving constellation of factors working in concert across billions of years. In this light, the faint young sun becomes not merely a problem to be solved, but a lens through which to view the resilience of life itself. A reminder that biological systems have always possessed the capacity to adapt, to thrive in conditions that our current models initially deemed impossible, and to reshape their planetary environment in ways that feed back into the very chemistry that sustains them. Early photosynthetic organisms, for instance, may have actively modified their atmospheric composition by producing oxygen, fundamentally altering the planet's energy balance and creating the conditions that would eventually allow more complex life to emerge, a process that transformed the very problem the faint young sun presented into an opportunity for biological innovation and evolution. Consider the fundamental paradox that haunts modern cosmology and stellar physics, a discrepancy so profound that it challenges our understanding of the universe's earliest moments and the processes that govern stellar interiors. When astronomers observe the abundance of lithium in the oldest stars of our galaxy, particularly those ancient population II stars that formed from the primordial hydrogen and helium left over from the Big Bang itself, they find consistently less lithium than theoretical models predict should exist. The Big Bang nucleosynthesis calculations, which have been refined over decades and remain some of the most robust predictions in theoretical physics, insist that the early universe should have produced roughly 3 times more lithium-6 than we actually detect in these ancient stellar atmospheres today. This is the lithium problem, and it represents a crack in our most fundamental understanding of universal origins. The mechanism underlying this apparent contradiction involves the complex interplay between primordial nucleosynthesis in the first few minutes after the Big Bang, when temperatures were high enough to forge light elements, and the subsequent destruction of lithium within stars through nuclear reactions at their cores. Stars gradually consume their lithium reserves through proton capture reactions that convert the element into beryllium and then helium, a process that occurs even in the relatively cool outer layers of certain stellar types. Yet the numbers simply do not align as they should, suggesting either that our calculations of primordial lithium production are fundamentally wrong, or that additional destructive mechanisms unknown to current physics operate within stars to eliminate this element more efficiently than we currently account for. What makes this paradox particularly vexing is that it persists despite intensive scrutiny from some of the world's most accomplished theoretical physicists and observational astronomers. Yet we continue forward with our cosmological models, accepting this inconsistency almost casually, incorporating minor adjustments and refinements while the core discrepancy remains unresolved, a fundamental mystery hidden within the peaceful light of ancient stars. The implications extend beyond mere numerical disagreement. If primordial lithium production was indeed different from our predictions, it would necessitate revising our understanding of the neutron-to-proton ratio in the early universe, fundamentally altering our picture of cosmic evolution itself. Meanwhile, proposed solutions ranging from exotic particle physics to revised nuclear reaction rates continue to emerge from laboratories and theoretical institutes, each offering a potential resolution, yet none achieving the overwhelming consensus required to declare the mystery solved. Recent observations from missions like Gaia and specialized spectroscopic surveys have only deepened the mystery by revealing that even younger stars show similar lithium depletion patterns, suggesting the problem may extend beyond primordial nucleosynthesis to challenge our understanding of stellar evolution itself, making this ancient light carry questions we are only beginning to formulate properly. The lithium problem thus stands as a humbling reminder that even our most carefully constructed models of fundamental physics contain gaps waiting to be bridged, and that the universe, in its infinite complexity, continues to present us with puzzles that demand both intellectual humility and renewed commitment to observation and theory working in concert to illuminate what remains hidden in the spectra of distant suns. Consider the profound temporal paradox that emerges when we examine the formation timescales of galaxies in our universe, a phenomenon that fundamentally contradicts our understanding of how quickly matter can organize itself under the influence of gravity alone. In our current cosmological models, we observe that galaxies in the early universe appear to have assembled themselves into remarkably complex and massive structures far more rapidly than the theoretical calculations suggest should be physically possible, with some of the most distant and therefore oldest galaxies showing evidence of having coalesced within merely a few 100 million years after the Big Bang itself. A time frame that seems incompatible with the leisurely pace at which gravitational processes typically unfold when dealing with the vast quantities of gas and dark matter required to build such enormous systems. The mathematics of gravitational collapse, when applied honestly and without adjustment, would suggest that gathering billions of stars worth of material from the primordial universe should require several billion years of patient accumulation and merging. Yet observations consistently reveal fully mature galaxies with developed structures and active supermassive black holes existing at cosmic epochs when they simply should not have had sufficient time to form. Our minds reconcile this contradiction through a curious psychological mechanism wherein we accept the introduction of speculative components like rapid dark matter condensation and invisible feedback mechanisms as placeholder explanations, allowing us to maintain the integrity of our theoretical framework without requiring fundamental revision, much like adjusting the scaffolding of a building rather than questioning whether the foundation itself is sound. We have gradually normalized this temporal impossibility through decades of scientific literature and educational presentation, treating the premature maturation of distant galaxies as merely another interesting puzzle awaiting a clever solution, rather than as a potential indicator that something profound about our cosmological understanding requires deep reconsideration. And this acceptance persists despite the nagging recognition that no mechanism yet proposed fully resolves the discrepancy without introducing additional layers of speculative physics that themselves require justification. The discovery of GNZ11, a galaxy observed as it existed merely 400 million years after the Big Bang with a mass comparable to our own Milky Way, exemplifies this tension most starkly. A system that should have required at least 10 times longer to assemble through conventional hierarchical merging scenarios, yet stands as irrefutable observational evidence that our timeline estimates are fundamentally misaligned with cosmic reality. This pattern repeats with troubling consistency across the population of early galaxies, suggesting not an anomaly but a systematic failure in our predictive framework. Yet rather than undertaking the difficult work of reconsidering our foundational assumptions about gravity's efficiency, dark matter's properties, or the initial conditions of the early universe, we have instead opted for the more comfortable path of incremental adjustment, introducing concepts like accelerated star formation rates and modified accretion physics that, while mathematically convenient, lack independent observational verification and serve primarily to preserve our existing theoretical edifice against mounting empirical challenge. The uncomfortable truth is that each new observation of an impossibly mature early galaxy does not prompt fundamental revision, but rather triggers a cascade of minor theoretical modifications, each one incrementally adjusting O. Consider the phenomenon of premature architectural commitment, wherein societies and individuals construct the foundational frameworks of their systems, institutions, and life paths long before the actual content, purpose, or direction of those systems has been adequately determined or understood. A student selects a major in their first semester of university, committing themselves to a rigid four-year structure before they have spent meaningful time exploring what that field actually entails or whether it aligns with their genuine interests and capabilities. A corporation builds an entire organizational hierarchy and reporting structure based on projections and theoretical efficiency models, only to discover years later that the actual work requires entirely different channels of communication and decision-making than the architecture allows. A government establishes constitutional frameworks and institutional designs in haste, creating rigid structures that become nearly impossible to modify as society evolves and discovers unforeseen needs that the original architecture never anticipated. The mechanism behind this paradox operates on the assumption that structure itself precedes and enables function, that by establishing the container first, the contents will naturally fill it and conform to its shape. We believe that boundaries and frameworks will somehow guide us toward the right choices, when in reality, we often discover that the structure we built was constraining rather than enabling, limiting rather than facilitating the organic growth of what we needed to become. This persists despite centuries of evidence demonstrating that the most successful systems and institutions evolved their structures through iterative experience rather than prescriptive design. Yet we continue to repeat this pattern because establishing structure provides psychological comfort, an illusion of control and forward momentum that feels better than admitting uncertainty and remaining flexible. We mistake the map for the territory, designing elaborate blueprints for journeys we haven't yet taken, then spending years trying to force our actual path to conform to lines drawn in advance. The tragedy is not that we build structure, but that we build it as if it were permanent, forgetting that the most resilient frameworks are those designed to be dismantled and rebuilt as our understanding deepens. Yet we rarely design with this flexibility in mind, instead creating structures that demand loyalty to their original logic even as that logic becomes obsolete. The university department that cannot adapt its curriculum because the building was designed for a specific pedagogical model, the marriage that persists in its original form because dismantling it feels like failure rather than evolution, the career path that continues forward by inertia alone. Long after both the person and the work have fundamentally changed, we become custodians of structures rather than their architects, defending systems that no longer serve us because we have confused the act of building with the act of commitment, treating the framework as if dismantling it would somehow invalidate the time we spent within it. The irony is that flexibility itself requires structure, but structure designed explicitly for revision, with built-in obsolescence and regular moments for reassessment, rather than the permanent architectures we so often default to creating. We might begin by asking not, what structure should this have, but rather, what structure would allow this to gracefully become something different? And building in explicit permission for transformation, making revision not an admission of failure, but the expected course of a system designed for genuine learning rather than mere stability. Imagine particles arriving at Earth's atmosphere traveling at velocities so close to the speed of light that they would require billions of years worth of the sun's entire energy output to accelerate them to such speeds. Yet they appear spontaneously from deep space with no discernible source. And when these ultra-high-energy cosmic rays collide with the upper atmosphere, they produce secondary particles that cascade downward in showers that can span kilometers across the ground below, creating detectable signals in arrays of sensors buried beneath the Earth or floating in space-based observatories. The most perplexing aspect of these cosmic rays is what physicists call the GZK cutoff, a theoretical limit suggesting that cosmic rays beyond a certain energy threshold should not be able to reach Earth because they would interact with photons in the cosmic microwave background radiation and lose energy over intergalactic distances. Yet astronomers continue detecting particles that exceed this cutoff, arriving from sources so distant and energetic that our current understanding of particle acceleration mechanisms cannot adequately explain their origin or their trajectory. The human mind tends to accept cosmic mysteries through a framework of deferred understanding, creating a comfortable conceptual space where we acknowledge that these particles exist, that they violate our expectations, and yet we organize our confusion into neat categories like unknown sources or exotic acceleration mechanisms, treating the inexplicable as merely the not yet explained. We have built vast detector networks and computational systems to measure these events, which provides a psychological anchor, transforming the fundamentally unknowable into measurable data points that feel more manageable, even though the measurements only deepen the paradox rather than resolve it. This normalization of the paradoxical persists because the phenomena remains remote from our everyday perception, belonging to a domain of reality that feels appropriately mysterious and therefore acceptable as genuinely perplexing, allowing us to rest comfortably within the knowledge that some aspects of the universe operate according to principles that transcend our current models. Yet this comfort dissolves the moment we consider that these particles might originate from events we have not yet theorized: black hole collisions, the decay of hypothetical particles from the early universe, or phenomena so foreign to our physics that we lack even the conceptual vocabulary to describe them, transforming our detectors from instruments of understanding into monuments to the limits of human knowledge. What makes this confrontation with limits particularly unsettling is that, unlike distant galaxies or theoretical quantum phenomena, these particles physically traverse our atmosphere and strike our detectors with undeniable presence, forcing us to acknowledge that the universe operates with a sovereign indifference to the boundaries of our comprehension. And that mysteries do not remain abstract when they arrive at Earth, traveling at 99.999999999% the speed of light. We find ourselves in the peculiar position of being struck by messengers we cannot fully decode, particles that carry information about the universe's most violent events yet arrive stripped of context, their origins obscured by the vast distances they traverse, leaving us to construct elaborate theories about magnetars and gamma-ray bursts and supermassive black holes in the desperate hope that attribution might substitute for comprehension. In 1966, physicists George Zatsepin and Vladimir Kuzmin independently discovered what should be a cosmic speed limit for ultra-high-energy cosmic rays, a theoretical barrier that would prevent particles from traveling across vast distances of the universe without losing energy through interactions with the cosmic microwave background radiation that permeates all of space. According to their calculations, cosmic ray particles with energies exceeding approximately 5 times 10 to the 19th electron volts should interact with photons from this ancient radiation field and produce pions, a process that would rapidly degrade their energy and prevent them from reaching Earth across intergalactic distances. This threshold became known as the GZK cutoff, and it represented what physicists believed to be an absolute cosmic boundary that nature herself would enforce through the fundamental laws of particle physics and electromagnetic interaction. Yet beginning in the 1960s and continuing through subsequent decades, observatories began detecting cosmic rays that appeared to exceed this supposed limit, arriving at Earth with energies far beyond what the theory predicted should be possible, events that seemed to violate the very mechanism that should have stopped them dead in their tracks. The psychological mechanism behind our acceptance of this violation rests upon a peculiar form of cognitive compartmentalization, where we maintain two simultaneously contradictory frameworks without fully confronting their incompatibility, acknowledging that the GZK cutoff remains theoretically sound, while accepting that nature somehow operates beyond its constraints. We have normalized this paradox by suggesting that perhaps unknown acceleration mechanisms exist closer to Earth, or that the sources of these ultra-high-energy particles might be far more exotic than previously imagined, effectively surrounding the violation with just enough theoretical scaffolding to make it feel less like a fundamental breakdown and more like an incomplete understanding requiring future refinement. The particles continue arriving from the cosmos, indifferent to our equations, and we continue observing them, patiently building new theories around their stubborn refusal to obey the old ones. This iterative dance between observation and theory, where each new discovery forces us to expand our conceptual frameworks, mirrors the history of physics itself, from the ultraviolet catastrophe to quantum entanglement, suggesting that nature's violations of our limits may be less about fundamental breakdown and more about the systematic incompleteness of any framework we construct to contain it. Perhaps the most humbling aspect of this pattern is that each generation of physicists has believed their framework to be nearly complete, only to discover that nature had been operating according to principles they had yet to imagine, a lesson that should temper our confidence in any current theory we hold as fundamental, while simultaneously fueling the methodical curiosity that drives science forward. The GZK cutoff violation thus stands as a reminder that our most confident predictions about cosmic boundaries may simply reflect the boundaries of our current knowledge rather than the boundaries of nature itself. And in this uncertainty lies both our humility and our hope. The recognition that the universe still holds mysteries profound enough to reshape the foundations of what we think we understand. As we detect these ultra-high energy particles arriving from distant galaxies, we are forced to confront the possibility that cosmic ray acceleration mechanisms operate at scales and intensities we have yet to comprehend, challenging us to venture beyond our current theoretical H. Deep within the mathematics of general relativity and quantum mechanics, there exists a theoretical paradox known as the Penrose-Hawking singularity, a concept that emerged from the collaborative work of physicist Roger Penrose and Stephen Hawking in their exploration of black hole thermodynamics and the nature of spacetime itself. The singularity in this particular formulation represents a point of infinite density and curvature where both the laws of physics as we understand them completely break down. Yet simultaneously, this breakdown occurs at a location that quantum mechanics suggests should not exist in the first place. Penrose proposed his cosmic censorship conjecture to suggest that naked singularities, those not protected by event horizons, cannot form in nature, while Hawking demonstrated through his groundbreaking calculations that black holes are not entirely black but emit radiation due to quantum effects near the event horizon, creating a paradox wherein the very existence of singularities becomes questionable as Hawking radiation slowly evaporates the black holes that were thought to contain them. The psychological mechanism that allows physicists to work with this paradox involves a kind of suspended disbelief, where they accept that current mathematical frameworks describe something that physically cannot be fully understood, treating the singularity as a placeholder for physics, yet to be discovered rather than as a genuine description of reality. We have normalized this profound breakdown in our understanding by compartmentalizing it, assigning singularities to the realm of extreme physics that operates under conditions so removed from ordinary experience that their logical impossibility feels almost acceptable, a way of saying that reality itself might be stranger and more incomprehensible than our current equations can capture. And so we drift into sleep contemplating a universe where the very foundations of cause and effect, of space and time, dissolve into mathematical abstraction at the heart of gravitational collapse, a dissolution that persists not despite its illogic, but perhaps because that illogic reflects something profoundly true about the limits of human comprehension itself. Yet in this acceptance of incomprehensibility lies a curious intellectual humility. We acknowledge that the universe may operate according to principles that transcend not merely our current instruments, but perhaps the very structure of human thought itself, and in that acknowledgement we find a strange peace with the infinite. This intellectual surrender, this acceptance of incomprehensibility, mirrors how we have learned to live with other fundamental mysteries. The measurement problem in quantum mechanics, the nature of dark matter, the origin of consciousness itself, each a singularity of understanding around which we have carefully constructed frameworks of mathematics and metaphor, hoping that someday the fog will lift, or perhaps recognizing that some fogs may be intrinsic to the landscape itself rather than mere limitations of our vision. In this way, the Penrose-Hawking singularity becomes less a failure of physics and more a mirror held up to the contours of human knowledge itself, a boundary marker indicating not where the universe ends, but where our current methods of inquiry reach their natural limits, inviting us to develop new languages and frameworks that might one day bridge the gap between the infinitely large and infinitely small, between gravity's classical whispers and quantum mechanics' probabilistic shouts. Until then, we continue to peer into the mathematical abyss, not with fear, but with the curiosity of explorers mapping territories that may forever resist complete cartography. Imagine a point in space where all the matter of a collapsed star has been crushed into infinite density. But unlike the singularities we believe must exist at the heart of black holes, this particular singularity possesses no event horizon surrounding it, no boundary of darkness beyond which light itself cannot escape, and therefore it remains theoretically visible to the outside universe in ways that should be physically impossible according to our current understanding of general relativity. This is the naked singularity, a mathematical solution that emerges from Einstein's equations with all the legitimacy of any other theoretical object, yet one that most physicists believe should never actually form in nature due to what Roger Penrose termed the cosmic censorship conjecture, a principle suggesting that the universe fundamentally prevents the existence of exposed singularities through some mechanism we have yet to fully understand or prove. The profound paradox lies in the fact that naked singularities are not forbidden by the equations themselves. Rather, they seem to be forbidden by a principle that appears to be more philosophical than mathematical, a cosmic rule of etiquette that we assume nature must follow rather than a law we can derive from first principles. The psychological mechanism that sustains this strange situation is our deep need to believe that the universe must be fundamentally orderly and predictable, that it must hide its most extreme infinities behind barriers where their infinite properties cannot corrupt the observable universe around them. And this assumption has become so deeply embedded in theoretical physics that we struggle to imagine its violation, even though nothing in the basic equations forbids it. We have normalized this uncertainty by treating cosmic censorship not as an open question, but as an established principle, teaching it in textbooks alongside verified facts, discussing its implications as though it were proven rather than conjectured. And this gradual shift from hypothesis to assumed truth reflects how theories can become foundational to our understanding simply through repeated assertion and our profound discomfort with the alternative. If we were to encounter evidence tomorrow that naked singularities could indeed form under certain exotic conditions, perhaps in the distant universe or in scenarios we have not yet imagined, we would face not merely a correction to our physics, but a confrontation with how profoundly our theoretical frameworks reflect our hopes and fears rather than nature's actual constraints, forcing us to rebuild our understanding from assumptions we did not even know we were making. Such a discovery would reveal that our most confident predictions about the universe's behavior emerge not from nature's laws themselves, but from our projection onto those laws of what we believe reality ought to be, a humbling recognition that the boundary between what we observe and what we assume we understand may be far more permeable than we typically acknowledge in our confident equations. Perhaps this is why the question of naked singularities haunts theoretical physics with such peculiar intensity, not because the mathematics is unclear, but because admitting their possibility would mean accepting that the universe might sometimes expose its deepest mysteries to observation, that nature might occasionally refuse to hide its infinities behind veils of event horizons, forcing us to confront questions about causality and predictability that we have only just begun to formulate. Yet in our reluctance to fully engage with this possibility, we may be protecting not physics itself, but our need to believe that observation and prediction remain forever separate domains that we can. Imagine the inverse of everything we know about black holes, a theoretical object so strange and counterintuitive that physicists struggle even to discuss it seriously. Yet the mathematics of general relativity suggests it should exist with the same logical certainty as its darker counterpart. A white hole would be a region of spacetime where matter and light are violently ejected outward in all directions, where the normal flow of causality appears inverted, where nothing can ever enter but everything continuously emerges, defying the one-way membrane that characterizes a black hole's event horizon. The fundamental paradox emerges from a deeply unsettling realization. If the equations of general relativity are truly time-symmetric, if they work equally well in both forward and backward temporal directions, then for every black hole solution describing matter falling inward, there must mathematically exist a corresponding white hole solution describing matter eternally streaming outward. Yet when astronomers scan the cosmos with their most powerful instruments, searching the darkness between galaxies and peering into the violent centers of active galactic nuclei, they find no evidence whatsoever of these theoretical objects, not a single confirmed white hole despite centuries of calculations predicting their inevitable existence. The paradox deepens when we consider that, according to classical general relativity, a white hole and a black hole connected through the same throat would form a wormhole, a bridge through spacetime, yet we have never observed such structures, raising the unsettling question of whether our most fundamental equations about gravity itself might be incomplete or misleading about the true nature of reality. Physics has normalized this absence through various theoretical mechanisms. Perhaps white holes are so unstable they collapse instantly. Perhaps they were created only in the earliest moments of the universe and have since vanished. Perhaps quantum effects we do not yet understand prevent them from ever existing in a stable form. Or perhaps most unsettlingly, our understanding of time's arrow and causality is fundamentally wrong in ways we have yet to discover. What makes this absence particularly haunting is that we cannot even rule out white holes through observation. The very nature of their outward-only causality means they would be nearly impossible to distinguish from ordinary stellar explosions or gamma-ray bursts, leaving us unable to confirm or deny their existence with any certainty, trapped in a theoretical blind spot where mathematics insists something should exist, but reality offers no way to verify it. Perhaps most troubling of all, some physicists have proposed that white holes might actually be black holes viewed backward in time, suggesting that the paradox itself reveals a fundamental confusion in how we perceive causality and temporal direction. That the universe might contain objects we interpret entirely differently depending on which temporal direction we observe them from, leaving us forever uncertain whether we have been searching for something that exists only as a mirror image of what we have already found. This temporal ambiguity strikes at the heart of why white holes remain perpetually beyond our grasp, not because they are necessarily absent from the universe, but because our very tools for observation may be fundamentally blind to their existence, condemned to mistake their signatures for the ordinary phenomena we have learned to recognize, leaving white holes as perhaps the most profound reminder that the universe may contain entire categories of phenomena we cannot access. Not because they violate physics, but because they violate our ability to perceive them. Imagine a singularity so powerful that it tears a hole in the fabric of spacetime itself, exposing the raw mathematical machinery of the universe in a way that should remain forever hidden from observation. This is the essence of cosmic censorship violation, a theoretical scenario where a naked singularity emerges without the protective veil of an event horizon to conceal it. According to Roger Penrose's cosmic censorship conjecture, formulated in 1969, the universe possesses a fundamental rule that prevents such violations from ever occurring in nature, maintaining an inviolable boundary between the knowable and the utterly incomprehensible. Yet physicists have discovered that under extreme conditions, such as the collision of black holes or the collapse of rotating matter at precisely calibrated angles, the mathematics permits these singularities to strip away their protective shrouds and exist in the open cosmos. The mechanism operates through a delicate balance of angular momentum and gravitational collapse, where sufficient rotation combined with specific density distributions could theoretically allow the singularity to outpace the formation of its surrounding event horizon, creating a window through which infinite curvature becomes directly observable rather than forever sealed away. What makes this paradox particularly unsettling is that if cosmic censorship violations occur, they fundamentally alter our understanding of causality and predictability in the universe. Yet despite decades of searching for evidence of naked singularities through gravitational wave detectors and astronomical observations, we have found no confirmed instances, suggesting that perhaps some deeper principle we have not yet understood actively prevents their formation. Or perhaps reality itself possesses an inherent tendency toward protection that transcends the equations we have written to describe it. Some researchers propose that quantum effects near the singularity might provide the missing mechanism, where the uncertainty principle itself could prevent the mathematics of infinite density from ever fully materializing, transforming what classical relativity permits into something fundamentally forbidden by the deeper laws of quantum gravity that we are only beginning to comprehend. If quantum gravity indeed enforces cosmic censorship at scales where classical physics breaks down, it would represent a profound reconciliation between relativity and quantum mechanics, a universe that protects itself from the very paradoxes our equations conjure into being, suggesting that mathematical possibility and physical reality operate under fundamentally different rules. This self-protective principle might explain why the universe appears so remarkably stable and rule-bound despite its underlying mathematical permissiveness. A cosmos that enforces its own censorship not through constraint, but through deeper symmetries we have yet to fully recognize, suggesting that what we call violations may simply be phenomena that nature has rendered impossible through mechanisms operating at scales beyond our current experimental reach. Perhaps the deepest implication is that cosmic censorship, whether enforced by quantum gravity or some other principle, represents nature's way of preserving the coherence of physical law itself, a mechanism ensuring that singularities remain mathematical abstractions rather than objects we could theoretically study, manipulate, or extract information from. which would demand an entirely new physics capable of managing infinities that our current frameworks treat as boundaries rather than territories to be explored. Imagine a sphere of any size, containing within it all the information that could possibly exist about everything inside its boundaries, and now consider that the total amount of information that sphere could ever hold is fundamentally limited not by how much space is available or how densely you could pack matter into it, but rather by the surface area of that sphere itself, a constraint so counterintuitive that it seems to violate everything we understand about how storage and information should work. The Bekenstein bound emerges from the intersection of thermodynamics, quantum mechanics, and general relativity, proposing that the maximum entropy of any physical system is proportional to its surface area rather than its volume, meaning that a vast cosmic region containing trillions upon trillions of stars and planets and potential information could theoretically be completely described by the information encoded on its outer boundary alone. This concept originated when physicist Jacob Bekenstein pondered black holes and realized that the event horizon of a black hole has an entropy proportional to its surface area, not the volume of space it encloses, and this observation suggested something far more profound about the nature of reality itself, that perhaps the universe operates according to a holographic principle where three-dimensional space might be nothing more than a projection of information encoded in lower dimensions. The psychological mechanism that makes us accept this paradox is our gradual acclimation to increasingly abstract physics, where we have already surrendered intuition about how reality works at both the quantum and cosmic scales. So when confronted with the notion that volume is somehow less fundamental than surface area, our minds have already been stretched so far that this additional impossibility simply adds another layer to the already incomprehensible nature of existence. We have normalized the Bekenstein bound by incorporating it into cutting-edge physics education and allowing it to influence how we theorize about black holes, quantum gravity, and the holographic universe, treating this boundary on information density as though it were as established and certain as classical thermodynamics, even though it represents one of the deepest unresolved questions about the architecture of reality itself. Yet the bound's influence extends beyond theoretical physics into how we conceive of artificial intelligence and information processing, suggesting that even the most ambitious computational systems are ultimately constrained by the thermodynamic properties of their physical substrate, meaning that no matter how we engineer our machines or expand our storage technologies, we can never escape this fundamental cosmic ledger written into the geometry of spacetime itself. This realization transforms how we think about the ultimate fate of information in the universe. Whether data encoded in matter will survive the heat death of the cosmos or dissolve into the void depends on whether it can be inscribed upon some final boundary we have yet to discover, making the Bekenstein bound not merely a constraint on physics, but a kind of cosmic accounting system that may determine whether anything we know, create, or preserve can persist beyond the universe's final moment. The question becomes whether consciousness itself, as an information processing phenomenon, might also be subject to this bound, suggesting that the very thoughts and experiences we believe make us unique are ultimately constrained by the thermodynamic limits of the physical matter that generates them, transforming the Bekenstein bound from an abstract mathematical curiosity into a potential explanation for the deepest mystery of existence: why anything persists. Imagine a cup of hot coffee sitting on a table in your kitchen, and you watch as it gradually cools down to room temperature over the course of an hour, its warmth dissipating into the air around it in an irreversible process that never reverses itself naturally. Yet when you examine the fundamental laws of physics at their most basic level, the equations that govern the motion of individual particles contain no preference for past or future. No built-in direction that would explain why heat flows from hot to cold, rather than spontaneously reversing to concentrate itself back into the cup. This is the thermodynamic arrow, the apparent directionality of time itself embedded in the second law of thermodynamics, which states that entropy in a closed system always increases. Yet this law emerges not from any fundamental asymmetry in the laws of physics, but rather from pure probability and the overwhelming number of possible disordered states compared to ordered ones. At the microscopic level, if you were to reverse the velocities of every single particle in that cooling coffee, the physics would work perfectly fine backwards, and yet we never observe this happening, suggesting that the arrow of time is not written into nature's deepest laws, but rather is a statistical ghost born from the fact that disorder is simply far more likely than order. And a collection of randomly moving particles is vastly more probable to drift toward maximum disorder than to spontaneously organize itself into the precise configuration required for heat to concentrate back into liquid warmth. Yet this insight, that time's arrow is fundamentally a story about probability rather than physics, reveals something profound about our place in the universe. We find ourselves in an extraordinarily improbable state, a low-entropy pocket of order in a cosmos inexorably moving toward equilibrium, and perhaps our very existence as conscious beings capable of observing this arrow is itself dependent on this temporary reprieve from maximum disorder, a fleeting island of complexity in an ocean destined for heat death. This is why memories exist only of the past and not the future. Our brains, like all physical systems, can only record information by increasing entropy, leaving a trail of disorder in their wake, and why we experience time as flowing inexorably forward, not because time itself flows, but because we are embedded in systems that can only move toward greater chaos. Making the arrow of time less a feature of the universe and more a consequence of being made of the same probabilistic stuff that comprises it. The paradox deepens when we consider that the Big Bang itself began in an extraordinarily low-entropy state, a condition of perfect order that seems to contradict the very principle it birthed, suggesting that the arrow of time may be less about the universe's tendency toward disorder and more about our position within a cosmos that started at its most organized and has been running down ever since. Making entropy not the universe's destination, but rather the measure of how far we've traveled from our beginning. And yet this raises a haunting question. If the universe began in perfect order and has been monotonically increasing its disorder ever since, then the arrow of time is not a mystery of physics, but rather a simple consequence of initial conditions. A cosmic accident that happened 13.8 billion years ago, meaning that everything we experience as the flow of time, from the warmth of that cooling coffee to the fading of our own memories, is merely the universe exhausting its original endowment of order. A slow unwinding of the cosmos's initial gift that will eventually leave us in a state of maximum entropy where nothing flows, nothing changes, and time itself becomes meanin. Imagine a closed container filled with gas molecules bouncing around in perfect chaos, each collision governed by the laws of physics that work identically whether time moves forward or backward, yet somehow the gas never spontaneously unmixes itself or returns to its original ordered state, and this contradiction sits at the heart of one of physics' deepest mysteries. A paradox first articulated by the Austrian physicist Joseph Loschmidt in 1876, when he challenged the growing conviction that entropy always increases and disorder always wins. The paradox emerges from a troubling asymmetry. The microscopic laws that govern individual particles are completely reversible, meaning that if you could reverse the velocity of every single molecule in that gas container at any given moment, they would retrace their exact paths backward through time, and yet the macroscopic behavior we observe is decidedly irreversible, as disorder increases with the passage of time and ordered systems naturally decay into chaos. Consider the mechanics of this contradiction more carefully. The mathematical equations describing how particles interact, whether through gravity or electromagnetic forces, contain no arrow of time, no preference for forward movement over backward, and theoretically, if you filmed a single collision between two molecules and then played it in reverse, the physics would still be perfectly valid and consistent. Yet when billions upon billions of particles interact simultaneously, their collective behavior strongly favors disorder, producing the unmistakable arrow of time that makes entropy increase, making yesterday different from tomorrow, and making memory and causality possible in our universe. The psychological resolution we have arrived at involves a subtle shift in perspective regarding what we mean by probability and initial conditions. Physicists now understand that while reversible microscopic laws do govern individual particles, the overwhelmingly vast majority of possible configurations are disordered ones. So the universe's initial conditions must have been extraordinarily special and ordered, and from that improbable beginning, the universe has been moving toward equilibrium ever since. Despite this resolution, a certain unease persists in our understanding because it requires accepting that the universe began in an incredibly unlikely state. That time's arrow emerges not from the laws themselves, but from statistics and initial conditions, and that the very distinction between past and future is in some sense a consequence of cosmic accident rather than fundamental law. leaving us contemplating a universe more subtle and strange than simple reversibility or simple irreversibility could suggest. This resolution shifts the burden of explanation from physics itself to cosmology and information theory, suggesting that the arrow of time is less a fundamental feature of nature's laws and more a consequence of how the universe happened to begin, a perspective that transforms entropy from a mere measure of disorder into a window onto the deepest origins of our cosmos. In this light, Loschmidt's paradox reveals itself not as a flaw in physics, but as a profound truth. That understanding why the universe behaves as it does requires us to grapple simultaneously with the laws governing matter and the far more mysterious question of why those laws operate within a cosmos that began in such an extraordinarily improbable state. This realization fundamentally reshapes how we think about causality itself. The fact that we remember the past but not the future, that we can influence tomorrow but not yesterday, emerges not from any asymmetry in the laws of physics, but from the statistical improbability of returning to lower entropy state. Consider the fundamental paradox that emerges when we attempt to conceptualize the very origin of time itself. For we find ourselves trapped within a linguistic and cognitive framework that seems to demand causation and sequence before the existence of the temporal dimension that would make such causation and sequence logically possible. When we ask what came before the beginning of time, we invoke a temporal framework that cannot exist prior to time's inception. Yet our minds instinctively reach for this impossible prior moment because consciousness itself appears to be fundamentally structured around the experience of sequential causation and the relationship between cause and effect. The human brain has evolved over millions of years to navigate a universe where time appears to flow in one direction, where events follow other events in predictable patterns, and where every action seems to require some preceding action that motivated it, creating a deeply ingrained neural expectation that nothing can simply begin without having been caused by something else that came before it. This creates an intellectual vertigo when we confront the singularity, the moment where physics suggests time itself emerged from conditions where time did not yet exist, a state so radically foreign to our experiential reality that we struggle to even formulate coherent questions about it without smuggling temporal assumptions into our inquiry. We normalize this paradox by accepting it as a boundary of human understanding, by designating it as a problem for theoretical physicists and cosmologists, while we continue our daily lives operating under the assumption that time is a simple, flowing medium through which events progress. Yet this normalization masks the profound strangeness lurking beneath every moment of existence. The paradox persists because we have no alternative framework for thinking, no way to step outside the temporal condition that defines our consciousness, leaving us forever bound to ask questions that may be meaningless, seeking answers about what came before when before itself is the very thing we are trying to understand. Perhaps this is why ancient cosmologies often posited cyclical rather than linear time, or why some contemplative traditions suggest that consciousness itself might be the fundamental ground from which temporal experience emerges, offering alternative frameworks that dissolve rather than solve the paradox by reconceptualizing what we mean by beginning itself. Yet even in recognizing these alternative frameworks, we remain caught in a peculiar bind. The very act of proposing that consciousness generates temporal experience requires us to think about how consciousness itself emerged, pushing the mystery back one layer without resolving it, suggesting that some questions may not await answers, but rather invite us to transform our understanding of what it means to ask. In this light, the question, when did time begin, transforms from a puzzle awaiting solution into an invitation to examine the architecture of thought itself, to recognize that our deepest inquiries often reveal not hidden truths about the universe, but the contours and limitations of the minds doing the inquiring. And perhaps this is the gift concealed within the paradox, that in chasing the origin of time, we discover not the answer to when the universe began, but rather a profound encounter with the boundaries of meaning itself, where the most honest response may be to sit with the question rather than grasp for a solution that dissolves the moment we examine it closely. Imagine standing at the edge of a temporal abyss, looking backward through time toward the moment of creation itself, only to realize that no matter how far back you peer, there is always something before it, an infinite recession of causality that stretches endlessly into a past that never truly begins. This is the infinite past problem, a paradox that emerges whenever we contemplate the origin of existence itself. For if everything that exists must have a cause, then that cause must itself have had a cause, and that cause before it must have had another cause, spiraling backward infinitely with no foundation, no ground floor, no primordial moment where causality simply ceases to require explanation. The philosophical mechanism underlying this paradox rests on our deeply intuitive assumption that causality is a fundamental feature of reality, that nothing simply exists without reason, that every effect must trace back to some prior cause, and this assumption feels so self-evident, so logically necessary, that we struggle to imagine how reality could operate any other way. Yet when we apply this principle consistently and rigorously, we arrive at an impossible conclusion. An infinite chain of causes stretching backward through time forever, with no beginning point to anchor the entire structure, which seems to violate our sense that sequences must have starting points. Physics and cosmology have attempted to resolve this through various mechanisms, suggesting that time itself may have begun with the Big Bang, or that quantum fluctuations require no prior cause, or that the universe exists in a self-contained mathematical structure needing no external explanation. Yet despite these theoretical solutions, the paradox persists in our collective consciousness as an unsettling reminder that our intuitions about causality may not map cleanly onto the deepest nature of reality. We have normalized this paradox by relegating it to the domain of metaphysics and theology, treating it as a question that science cannot answer rather than recognizing it as a fundamental challenge to our assumptions about how existence must work. And in doing so, we allow ourselves to continue living and thinking as though causality is absolute and complete, even as we acknowledge that infinity stretches backward behind every moment we observe. Yet this acceptance comes at a cost. We live within a conceptual framework that demands explanation for everything except the one thing that requires it most urgently, the existence of existence itself, leaving us perpetually suspended between the demand for rational grounding and the impossibility of ever providing it, caught between two equally unbearable alternatives of infinite regress and brute fact. Perhaps this is why we instinctively reach for cyclical cosmologies, eternal universes, or divine uncaused causers, not because these solutions are logically superior, but because they offer psychological relief from the vertigo of standing at the edge of that temporal abyss, trading one form of mystery for another that feels less disorienting. Yet even in choosing our preferred mystery, we remain fundamentally unchanged, still seeking solid ground in a cosmos that may offer none, still asking why to questions that the structure of causality itself may render unanswerable, still hoping that somewhere in the darkness behind all moments, there exists a reason sufficient to explain why there is something rather than nothing, even as eternity whispers that such a reason may be precisely what can never exist. And so we persist in this strange dance with infinity, asking our unanswerable questions not because we expect resolution, but because the asking itself is what makes us human, creatures uniquely tormented by our own capacity to are. Imagine the most violent and energetic explosion the universe has ever produced, a cataclysm so intense that in just a few seconds it releases more energy than our sun will emit across its entire 10 billion-year lifespan, and this phenomenon is called a gamma-ray burst, an astronomical event so paradoxical that it seems to violate our fundamental understanding of how matter and energy should behave in the cosmos. When massive stars collapse at the end of their lives, or when two neutron stars spiral into one another and merge, they create a singular moment of incomprehensible power, releasing a focused beam of gamma radiation that travels outward at the speed of light. And because this beam is so tightly collimated and directed, it appears incredibly bright to observers positioned along its path, bright enough that we can detect these bursts from billions of light years away. From the most distant reaches of the observable universe, yet the paradox emerges when we consider the physics involved. For the energy densities are so extreme that they should theoretically create a fireball that expands uniformly in all directions, not a narrow jet. And the acceleration mechanisms required to achieve such relativistic speeds and maintain such extreme beaming should be physically impossible according to conventional magnetohydrodynamic theory. And yet observations consistently show that these jets are remarkably stable and efficient, converting the rotational energy of collapsing stars into directed radiation with an elegance that our current models struggle to fully explain. The psychological mechanism that allows us to accept this paradox is our tendency to treat extreme phenomena as somehow operating under different rules, as though the universe has separate instruction manuals for ordinary events and catastrophic ones, when in reality the same laws should apply everywhere, and we convince ourselves that future observations and refined theoretical frameworks will eventually explain these jets. That they will become rationalized and incorporated into our understanding as though they were always sensible, when in fact we have normalized our ignorance into a form of scientific patience, accepting that we observe these phenomena repeatedly, that they are reproducible and measurable, yet we do not truly comprehend the mechanism that makes them possible. This uncertainty itself becomes a kind of knowledge, a precise mapping of the boundary between what we can measure and what we cannot yet explain. And perhaps in studying gamma-ray bursts, we are not merely observing distant explosions, but confronting the limits of human comprehension itself, the point where the universe's complexity exceeds our current theoretical frameworks and reminds us that understanding is always provisional, always subject to revision when new evidence arrives. And so when astronomers detect a gamma-ray burst's characteristic X-ray afterglow fading across the electromagnetic spectrum, they are witnessing not merely the death of a star, but a humbling reminder that the universe continues to operate at scales and intensities that transform our most confident equations into provisional sketches, useful tools that capture only fragments of a far more intricate reality than we have yet learned to perceive. Yet it is precisely this humility that drives further investigation, for each gamma-ray burst detected becomes another data point in humanity's slow accumulation of cosmic knowledge, another opportunity to refine our instruments and theories until the inexplicable gradually transforms into the understood, a process that has defined scientific progress since we first began looking upward at the night sky and dared to ask not merely what we see, but why. Imagine a star so dense that a teaspoon of its material would weigh as much as all the mountains on Earth combined, and then imagine that this star has collapsed further into what we call a magnetar, an object so small it could fit inside a city, yet possesses a magnetic field so extraordinarily powerful that it defies our conventional understanding of electromagnetic forces entirely. These neutron stars, particularly magnetars, generate magnetic fields that reach strengths of 10 to the power of 15 Gauss, numbers so incomprehensibly large that they seem to exist outside the realm of physical possibility. Yet they demonstrably do exist, and we observe their effects across vast distances of space. The paradox deepens when we consider that, according to our established laws of physics, no magnetic field should theoretically be able to achieve such intensities without requiring energy input so enormous that it would violate conservation principles. Yet magnetars appear to generate and maintain these fields with no apparent external energy source, as if they are simply violating the rules we thought were fundamental to reality itself. The psychological mechanism at work here involves our tendency to compartmentalize extraordinary phenomena into special categories, to say that magnetars are somehow exceptions rather than challenges to our understanding. And we have developed elaborate theoretical frameworks involving quantum effects and relativistic plasma dynamics, specifically to rationalize how these objects can exist without technically breaking the laws we hold sacred. We have essentially created intellectual scaffolding around the paradox, rather than confronting what it might mean that nature is producing magnetic fields of such impossible intensity that they would rip apart any material object brought near them. Fields so powerful they could distort atoms themselves and strip electrons from atoms at distances of thousands of kilometers. What is remarkable is that we have normalized this impossibility so thoroughly that we discuss magnetar fields with the same casual certainty we use when discussing ordinary stars, never pausing to fully acknowledge the conceptual violation they represent, the way they seem to operate according to a physics we have not yet fully grasped, suggesting that perhaps our framework for understanding electromagnetism remains fundamentally incomplete despite all our confidence in it. Perhaps the most unsettling aspect is that magnetars may not be unique violations, but rather extreme manifestations of principles we encounter throughout nature, phenomena that consistently push beyond our theoretical limits and force us to recognize that our models are descriptions of a subset of reality, not descriptions of reality itself, leaving us to wonder what other impossible fields and forces await discovery in the cosmos. The history of physics is littered with such humbling moments, from the discovery that light could behave as both wave and particle to the revelation that time itself is relative, each forcing us to expand our conception of what is possible, and magnetars stand as contemporary reminders that we remain perpetual students of a universe far more imaginative than our theories allow. Yet even as we develop new theoretical frameworks to accommodate magnetars, we might ask whether our impulse to explain away the impossible is itself a form of intellectual complacency, a way of preserving our sense of mastery over nature rather than sitting with genuine uncertainty about the fundamental forces that structure reality. Deep within the cosmos, neutron stars spin with the precision of cosmic clockwork, rotating hundreds of times per second and emitting beams of radiation that sweep across space like lighthouses of the extreme universe. These pulsars are among the most regular objects known to science, their rotation periods so stable that astronomers have used them as celestial timekeepers for decades, comparing their reliability to atomic clocks on Earth. Yet periodically, without warning and without any apparent external cause, these stellar monuments to regularity experience what scientists call glitches, sudden and unexplained increases in their rotational speed that violate our understanding of how isolated spinning objects should behave. A pulsar might spin at a perfectly constant rate for years or even centuries, and then abruptly, its spin accelerates slightly, as though some invisible hand has given it an additional push, before it gradually returns to its normal deceleration pattern over weeks or months. The mystery deepens when we consider that pulsars exist in isolation, surrounded by the vacuum of space where no external torques should logically be able to act upon them. Yet these glitches recur in patterns that suggest something profound is happening within the neutron star itself, perhaps related to the superfluid interior that theoretical physics predicts should exist at such extreme densities. Scientists have proposed that the interior of these neutron stars might contain layers of superfluid matter that can move independently of the solid crust, and during a glitch, these internal layers might suddenly couple and transfer their angular momentum to the outer shell, causing the observed acceleration in spin rate. Yet this explanation only deepens the paradox, because we cannot directly observe these internal structures or verify whether this mechanism truly operates as we imagine. The persistence of these glitches, occurring in multiple pulsars across the observable universe and repeating in the same objects throughout time, suggests that something fundamental about our models remains incomplete or incorrect, and yet we continue to refine our instruments and observations, accepting that the universe contains phenomena that resist our current frameworks of understanding. Perhaps the most humbling aspect of pulsar glitches is that despite decades of dedicated observation and increasingly sophisticated theoretical models, each new glitch event reminds us that neutron stars, those extreme laboratories where matter reaches densities beyond anything we can recreate on Earth, still guard secrets about the fundamental nature of physics itself, challenging us to listen more carefully to what the universe is trying to teach us. As astronomers continue to monitor pulsars like the Crab pulsar and Vela pulsar, objects that have gifted us thousands of glitch events to study, they recognize that understanding these phenomena may ultimately reveal how matter behaves under conditions so extreme that they cannot be replicated in any terrestrial laboratory, making pulsars not merely celestial curiosities, but essential windows into physics at its most fundamental level. The recent detection of glitches in millisecond pulsars, some of which rotate over 700 times per second, has forced theorists to reconsider whether superfluid coupling alone can explain all observed phenomena, or whether we must invoke additional mechanisms such as magnetic field interactions or the presence of exotic quark matter in the neutron star core. In this way, pulsar glitches have become a cosmic puzzle that drives innovation in both observational astronomy and theoretical physics, reminding us that the universe's most profound secrets often hide within the most precise and predictable object. Imagine receiving a signal from the cosmos that lasts only milliseconds, a burst of radio energy so intense and so brief that it arrives and vanishes before your instruments can even fully process what has occurred. Yet this signal carries as much energy as our sun produces in an entire day, compressed into a flash that barely registers on human scales of time and perception. These are fast radio bursts, FRBs as astronomers call them, transient phenomena that appear randomly across the sky with no discernible pattern, no warning, and no obvious explanation for their origin or mechanism. The first fast radio burst was detected in 2007, buried within archival data that had been collected years earlier, and since that initial discovery, hundreds more have been catalogued, each one arriving from different parts of the universe, some repeating in irregular cycles, while others appear only once and never again. The physical reality of these bursts defies immediate comprehension because they should not exist in the forms we observe them. They violate conventional expectations about what cosmic phenomena should be capable of producing, and their energetics remain fundamentally mysterious despite decades of investigation and increasingly sophisticated detection methods that now allow us to catch these events as they happen rather than discovering them in old recordings. The psychological mechanism that allows us to normalize such profound cosmic weirdness stems from our tendency to compartmentalize the inexplicable into the category of things we simply haven't figured out yet, framing mysteries as temporary gaps in knowledge rather than genuine violations of our understanding of reality itself. We convince ourselves that fast radio bursts must have conventional origins, that somewhere in the universe there exists some neutron star or magnetar or binary system undergoing some exotic collision or gravitational event that naturally produces these bursts, and we construct elaborate theoretical models to explain them. Yet none of these models fully accounts for all the observed characteristics. None of them explains why some bursts repeat while others do not. And none of them addresses why we detect such events with apparent randomness scattered across the observable universe. We have created committees of dedicated researchers and named candidate explanations with scientific terminology. We have built new telescopes specifically designed to catch these events, and we have integrated FRBs into our cosmological understanding as merely another puzzle piece. Yet the fundamental strangeness persists. The fact that we can observe such tremendous energy releases that last only fractions of a second and then disappear completely, leaving behind no persistent source. No continuing signature, no object we can point to and study further. Despite our collective need to resolve this mystery through conventional means, we continue to operate within a framework where fast radio bursts simply exist as accepted phenomena, anomalies that have been normalized into our catalog of cosmic knowledge, integrated into our databases and our research initiatives without fundamentally challenging our assumptions about how the universe actually works. And this represents a strange equilibrium where we acknowledge the profound strangeness of these bursts, while simultaneously treating them as manageable scientific problems awaiting eventual solutions, rather than as evidence that our understanding of cosmic physics may be far more limited than we generally assume. Yet perhaps this comfortable ambiguity serves a purpose, allowing us to maintain productive curiosity rather than paralyzed bewilderment in the face of cosmic phenomena that may ultimately require us to expand our. Consider the phenomenon of superluminal jets, where material ejected from the cores of distant galaxies and active galactic nuclei appears to move faster than the speed of light itself, a velocity that should be physically impossible according to Einstein's theory of special relativity. Yet astronomers have observed these jets moving at apparent speeds that reach 5, 10, sometimes even 20 times the speed of light when measured across the sky. The mechanism behind this apparent violation is not actually a violation at all, but rather an optical illusion born from the geometry of space and time and the finite speed at which light itself travels to reach our telescopes here on Earth. When a jet is ejected at nearly the speed of light at an angle close to our line of sight, the material at the front of the jet races toward us while simultaneously moving sideways across the sky. And because this material is traveling almost as fast as the light it emits, the light from successive positions along the jet's path arrives at our instruments separated by far less time than the actual time that has passed, creating the illusion of motion faster than light itself. We measure this apparent motion in angular displacement across the sky divided by the time interval between observations, but that time interval is artificially compressed by the relativistic beaming effect, making the jet appear to traverse vast distances in impossibly short periods. What makes this phenomenon so psychologically compelling and worthy of contemplation is how it demonstrates the strange marriage between observation and reality, how the universe can behave in ways that seem to mock our fundamental understanding of physics while remaining entirely consistent with that same understanding when examined from the proper perspective. We have normalized this paradox in our minds by accepting the mathematical explanation and moving forward with our observations. Yet there remains something deeply unsettling about watching objects that we know cannot possibly be traveling faster than light appear to do exactly that across our instruments night after night, year after year, as if the universe delights in presenting us with riddles dressed as contradictions. These jets emanating from supermassive black holes spinning at near-relativistic speeds and powered by magnetic fields of unimaginable strength, remind us that the cosmos operates according to principles both elegant and counterintuitive, where the most extreme environments produce phenomena that test the very limits of our perceptual and theoretical frameworks. The jets of M87, observed by radio astronomers for decades, and those erupting from Centaurus demonstrate this effect with particular clarity, their apparent velocities shifting dramatically depending on the angle at which we happen to view them from our vantage point in the cosmos. A humbling reminder that much of what we perceive depends fundamentally on where we stand. The detection of superluminal motion across thousands of active galactic nuclei has become a standard tool in modern astronomy, allowing us to constrain the Lorentz factors of relativistic jets and map the structure of regions too small to resolve directly. Yet each observation carries with it the philosophical weight of a cosmic illusion, a reminder that seeing is not believing in any simple sense. The temporal distortion inherent in these observations, where we measure time intervals that are compressed by factors matching the relativistic beaming, creating a kind of cosmic perspective shift, reveals how profoundly our measurements are entangled with the geometry of observation itself, a lesson that extends far beyond jets to illuminate the fundamental nature of how we extract meaning from an indifferent. Consider the observable universe as we understand it through our most powerful telescopes and our most refined measurements of cosmic microwave background radiation, that ancient light which has traveled toward us from the earliest moments after the Big Bang itself. When cosmologists examine this radiation arriving from opposite sides of the sky, from regions so vastly separated that light itself could not have traveled between them in the time since the universe began, they observe something profoundly puzzling. These distant regions possess nearly identical temperatures and densities, as though they had somehow communicated and equilibrated their properties despite their cosmic isolation. This observation forms the crux of what physicists call the horizon problem, a conceptual paradox that sits at the foundation of modern cosmological theory. The mechanism underlying this puzzle operates through the principle of cosmic horizons, the maximum distance from which light or information could have reached us since the moment of the Big Bang itself, a boundary that expands outward through space and time as the universe ages and grows. Regions lying beyond each other's horizons cannot have exchanged information, yet they display an uncanny homogeneity that seems to demand prior communication or an extraordinary coincidence of initial conditions. The inflation hypothesis was proposed specifically to resolve this conundrum, suggesting that in the universe's first fraction of a second, spacetime underwent exponential expansion so rapid and so extreme that all observable matter originated from a single, causally connected region before being inflated to cosmic scales. This mechanism would explain why distant regions appear so similar. They were once close enough to equilibrate before inflation stretched them apart to their present separation. Yet this solution introduces its own layers of mystery, for inflation itself requires extraordinarily fine-tuned initial conditions and raises questions about what drove this cosmic acceleration and how it eventually stopped. The persistence of this paradox, even with inflation as our leading explanation, reflects a deeper truth about cosmology, that our understanding of the universe's origins remains incomplete and provisional, constrained by the fundamental limits of observation and the mathematical frameworks through which we interpret that observation. Modern cosmological observations, particularly measurements of temperature fluctuations in the cosmic microwave background with unprecedented precision, continue to reveal patterns consistent with inflation, while simultaneously raising new questions about whether inflation itself merely displaces the fundamental puzzle to an earlier, perhaps inaccessible epoch of cosmic history. Some physicists have proposed that inflation itself may have been eternal, extending infinitely into the past, which would push the ultimate origin question beyond the reach of science entirely. Others suggest that multiple universes underwent their own inflationary episodes, each with distinct physical laws, transforming the horizon problem from a puzzle about our cosmos into a question about the landscape of all possible universes. In either case, the problem that motivated inflation, explaining cosmic uniformity, may ultimately reflect not a flaw in our understanding, but rather a fundamental boundary beyond which physical explanation cannot venture. This recognition invites a humbling perspective. The horizon problem may represent not a gap in our knowledge waiting to be filled, but rather an encounter with the fundamental asymmetry between what the universe permits us to observe and the totality of what exists beyond our cosmic reach. Imagine a universe that never stops expanding, not just in the way we observe it today, but infinitely, eternally, without end or limit, where the process of cosmic inflation that occurred in the first fraction of a second after the Big Bang never truly ceased, but instead continues in regions far beyond our observable horizon, creating pocket universes within pocket universes in an endless cascade of creation that defies our intuitive understanding of beginnings and endings. In this theoretical framework proposed by physicist Andre Linde, inflation doesn't simply turn off after inflating our universe to its current size. Rather, it persists in pockets of spacetime scattered throughout an ever-expanding cosmic foam, each pocket potentially containing its own universe with entirely different physical laws, fundamental constants, and environmental conditions that bear no resemblance to our own. The mechanism underlying eternal inflation rests on quantum fluctuations occurring within the inflaton field, a theoretical quantum field that drives cosmic expansion, where random quantum events can trigger new regions of space to begin inflating, while other regions reach completion and settle into a state we recognize as our own universe. This process creates a strange recursive reality where the act of creating universes becomes self-perpetuating, each universe potentially spawning countless others through the same mechanism, a branching tree of existence that extends backward and forward through time in ways that challenge our comprehension of causality itself. What makes eternal inflation so deeply unsettling as a concept is not merely its mathematical elegance or its grounding in legitimate physics, but rather our strange acceptance of a cosmos fundamentally indifferent to our existence, one where countless realities bloom and perish beyond our awareness, where the universe we inhabit represents merely one infinitesimal corner of an incomprehensibly vaster whole. And yet we persist in treating our observable universe as though it were singular and complete. The implications extend beyond mere cosmology into the realm of meaning itself. If our universe is but one bubble among infinite others, each with its own history and physical laws, then the particular conditions that allowed for life, consciousness, and ultimately the emergence of beings capable of pondering their own existence become simultaneously more precious and more arbitrary, a cosmic accident repeated infinitely across the multiverse, yet never guaranteed to occur in quite the same way. The question then becomes whether understanding this cosmic vastness diminishes or elevates our sense of wonder. Does knowing we are likely one of infinite conscious observers scattered across an infinite multiverse make our individual perspective meaningless, or does it suggest that consciousness itself, the universe's capacity to know itself, represents the deepest commonality binding all these disparate realities together? Perhaps the most radical implication of eternal inflation is that it reframes the ancient philosophical question of why there is something rather than nothing. In a multiverse where inflation never truly ceases, the emergence of universes becomes not an exception requiring explanation, but rather the default state of reality itself, where the absence of universes would be the true anomaly demanding justification. In this inverted cosmological logic, the burden of proof shifts from explaining existence to explaining non-existence, suggesting that universes proliferate not because of some extraordinary cosmic accident, but because the laws of quantum mechanics themselves encode a fundamental imperative toward expansion and creation. Imagine the vast, infinite expanse of the universe stretching endlessly into the future, long after all stars have burned out, after all black holes have evaporated through Hawking radiation, after the last particles of matter have decayed into pure energy and dispersed into the cold void. In this infinitely distant future, the universe reaches a state of perfect thermal equilibrium, a condition of maximum entropy where nothing distinguishes one region of space from another. And yet, according to the laws of statistical mechanics and thermodynamics, if you wait an incomprehensibly long time, random quantum fluctuations will occasionally create temporary pockets of organization from the chaos. One of the most disturbing implications of this principle is that eventually, purely by chance, the atoms and particles scattered throughout this dead universe could spontaneously arrange themselves into the exact configuration that constitutes a conscious brain, complete with all the neural patterns and electrochemical processes necessary to produce a subjective experience of awareness. This theoretical entity, named after physicist Ludwig Boltzmann, who first grappled with these implications, represents a brain that springs into existence fully formed through nothing but blind statistical probability, existing for a brief moment of awareness before dissolving back into entropy. The psychological weight of this paradox emerges from a troubling logical consequence. If such fluctuations are possible, and if infinite time exists for them to occur, then statistically speaking, most conscious beings in the universe should be these momentary Boltzmann brains rather than beings like us who emerged through billions of years of evolutionary development within stable, ordered physical systems. Our very existence as observers with continuous histories becomes vastly improbable compared to the likelihood of random brain fluctuations, yet we find ourselves firmly rooted in an ordered cosmos with a clear past and causal history. This paradox persists within physics and philosophy despite having no resolution, forcing us to confront the possibility that our assumptions about consciousness, probability, entropy, or the nature of the universe itself might be fundamentally incomplete or incorrect. Perhaps the most unsettling aspect is that this problem suggests our intuitive confidence in causality and evolutionary history. The very foundations upon which we build our understanding of reality may be nothing more than a comforting illusion sustained by our particular vantage point in an incomprehensibly vast cosmos. If we cannot trust that our memories and experiences reflect genuine causality rather than statistical accident, then the very enterprise of science, which depends upon the assumption that the past genuinely happened and constrains the present, becomes philosophically unstable, forcing us to either accept that we possess special knowledge of our own causal history or admit that our scientific understanding rests upon an unprovable and perhaps unprovable assumption about the fundamental nature of reality. Yet in the end, this paradox may reveal less about the universe and more about the limits of our reasoning. By taking statistical mechanics to its logical extreme, we encounter a reductio ad absurdum that suggests certain theoretical frameworks, however mathematically elegant, break down when extended beyond their intended domain of applicability, reminding us that even our most fundamental physical theories require boundary conditions and assumptions about which questions are worth asking. Imagine a universe where the act of observing something fundamentally changes what it is, and imagine further that every time you measure a quantum system, the universe splits into multiple versions where each possible outcome actually occurs simultaneously, each one equally real and equally valid. This is the essence of the measure problem in the many worlds interpretation of quantum mechanics, a paradox so profound that it undermines our most basic understanding of probability itself. In standard quantum mechanics, we accept that before measurement, particles exist in a superposition of multiple states, and the act of measurement collapses this superposition into a single outcome with specific probabilities defined by the wave function. The many worlds interpretation rejects wave function collapse entirely and instead proposes that every possible outcome actually happens in a branching multiverse, where each branch represents a complete universe containing an observer who experiences that particular outcome. But here is where the measure problem emerges like a ghost in the mathematical machinery. If every outcome actually occurs with equal ontological weight, if every branch is equally real and equally existent, then what exactly does probability mean anymore? Why do we observe outcomes that match quantum mechanical probabilities rather than all outcomes being equally frequent in our experience? How can probability even exist when all possibilities are realized? We have normalized this paradox through mathematical sleight of hand, developing increasingly sophisticated formalisms to extract probabilities from a framework that philosophically denies their necessity. Yet we remain profoundly uncertain whether these mathematical tools actually solve the problem or merely obscure it. The measure problem persists as a fundamental conceptual crisis precisely because it reveals a gap between our mathematical descriptions of reality and our intuitive understanding of what probability means when all possible worlds genuinely exist. Consider a coin flip in the many worlds framework. Both heads and tails occur in separate branches, yet we insist we observe heads with probability 1/2. But 1/2 of what exactly when both outcomes are equally real? This is not merely a philosophical puzzle. It strikes at the heart of whether probability is something fundamental to nature or merely a description of our ignorance about which branch we happen to inhabit. The unsettling implication is that probability might be fundamentally subjective, a feature of our epistemic position within the branching tree rather than an objective property of the multiverse itself, which transforms the measure problem from a technical puzzle into a question about the very nature of meaning and perspective in a universe where all possibilities are real. If the subjective nature of probability is correct, then observers in different branches might rationally assign different probabilities to their own experiences despite inhabiting an objectively symmetric multiverse. A conclusion so alien to our scientific intuitions that it forces us to reconsider whether probability was ever truly objective at all, or whether we simply mistook our ignorance for a feature of nature itself. This realization suggests that the measure problem might ultimately be unsolvable not because our mathematics is inadequate, but because we are asking the wrong question. We are searching for an objective fact about probability in a framework where the only facts that exist are the subjective experiences of conscious observers distributed across an infinite tree of branching realities, each one convinced of their own unique place in an objectively indifferent multiverse. Consider the moment when a quantum system, existing in a superposition of multiple states simultaneously, encounters the larger environment and suddenly collapses into a single definite state, a phenomenon we call decoherence. And imagine this process occurring at the cosmic scale, where entire universes might exist in quantum superposition before some unknown mechanism forces them into classical reality. The real-life situation involves particles that can theoretically exist in all possible states at once until they interact with their surroundings. Yet when we scale this up to galaxies, black holes, and the universe itself, we find ourselves in a conceptual space where nothing should logically maintain coherence given the constant bombardment of environmental information, and yet somehow the universe persists as a seemingly singular, definite reality rather than a constantly fluctuating probability cloud. The psychological mechanism behind our acceptance of this paradox stems from the human tendency to project familiarity onto scales we cannot directly observe, allowing us to pretend that the rules governing the quantum realm simply do not apply once objects become large enough, even though no fundamental law actually permits such an exception, and the transition itself remains one of physics' deepest unsolved problems. We have normalized this apparent contradiction by separating quantum mechanics and classical physics into distinct domains, creating an artificial boundary that protects our intuitions from the uncomfortable truth that reality at all scales should theoretically behave according to the same underlying quantum rules. Yet somehow macroscopic objects refuse to exhibit the superposition, entanglement, and probabilistic nature that quantum theory predicts they should display. The universe maintains its coherence as a singular observable fact, despite the theoretical prediction that it should have decohered into an incomprehensible blur of competing realities. And we continue studying this mystery while simultaneously accepting that our everyday experience represents something that, by the strictest interpretation of quantum mechanics, should not be able to exist in its present form. Perhaps the deepest irony is that we rely on quantum mechanics to explain the formation of stars and galaxies in the early universe. Yet quantum mechanics simultaneously predicts that such large-scale structures should have immediately decohered into classical impossibility, suggesting that the very physics we use to understand cosmic origins contains within it the seeds of its own contradiction. This unresolved tension, that quantum rules created the cosmos while classical rules preserve it, remains the ghost in the foundation of our understanding, a fundamental inconsistency we have learned to work around rather than resolve. We construct elaborate mathematical frameworks to bridge this chasm: quantum to classical transitions, decoherence timescales, environmental interaction models. Yet each solution merely relocates the problem rather than eliminating it, transforming the question from "why doesn't the universe decohere?" into "at exactly what size does decoherence become irrelevant?" A question we answer not through fundamental understanding, but through empirical observation of where our equations stop matching reality. The boundary we draw between quantum and classical becomes less a discovery of nature and more a confession of our limitations. We mark the edge of our theoretical understanding and call it the edge of quantum behavior itself, a sleight of hand that has proven remarkably effective at making predictions while leaving the fundamental mechanism of reality's transition from possibility to fact suspended in permanent obscurity. Imagine standing before a locked box containing a single particle, and you are told that before you open it, the particle exists in a state of pure probability, simultaneously in multiple positions at once, described mathematically by what physicists call a wave function that spreads across all possible locations with measurable likelihood. The moment your eyes open that box, the instant your measurement apparatus interacts with the system, something profoundly strange occurs. The wave function collapses instantaneously, and the particle snaps into one single definite location, as if the very act of observation itself forces reality to make a choice it was previously avoiding. This is the paradox that has troubled the greatest minds in physics for nearly a century, because the mathematics works perfectly to describe the probabilities before measurement. Yet nowhere in those same equations does it explain how or why observation should cause such a dramatic, instantaneous transformation of what is physically real. The particle was not hiding in one spot all along waiting to be found. The evidence suggests it genuinely existed in all places simultaneously, and your measurement somehow compels the universe to decide. What makes this intellectually devastating is that the mathematics offers no mechanism for this collapse, no physical process, no explanation for why consciousness or measurement or interaction should cause wave functions to behave this way. Yet experiments confirm again and again that this is precisely what happens in our universe. We have accepted this paradox, incorporated it into our fundamental understanding of reality, and simply moved forward despite the fact that wave function collapse suggests measurement and observation are not passive recording devices, but active participants in creating the concrete reality we perceive, which challenges everything we assume about the objective existence of a world independent of observers. Some interpretations suggest that consciousness itself plays a role in collapse, while others propose that decoherence through environmental interaction gradually narrows possibilities without requiring a sharp boundary, yet none fully resolves why the universe behaves as if reality requires a witness. This mystery remains one of the deepest questions in physics, whether the universe is fundamentally indeterminate until observed, or whether our current mathematics simply lacks the framework to describe what actually happens at the moment of measurement. What we do know is that this ambiguity has profound implications. If reality truly requires observation to become definite, then the universe before conscious life emerged existed in a radically different state, and the act of life itself, of eyes opening and minds perceiving, may have fundamentally altered what was possible, suggesting that observers are not merely discovering a pre-existing reality, but are essential participants in its actualization. This realization inverts our intuition about science itself. Rather than physics revealing a world that exists independently of us, it suggests that the universe and observer are bound in a reciprocal relationship where neither can be fully understood in isolation, making the question of what is real inseparable from the question of who is asking. Perhaps the most unsettling implication is that this isn't merely philosophical speculation. It's encoded in the mathematics we use to make predictions about atoms, light, and the subatomic particles that compose everything we touch, see, and are, meaning that the apparent strangeness of wave function collapse isn't a flaw in our understanding, but a feature of reality itself that we've learned to calculate with perfect precision, even as its fundamental meaning. Consider the origin of Earth's moon, a celestial body that orbits our planet at a distance of approximately 238,000 miles, exerting gravitational influence that stabilizes our planet's axial tilt and generates the tides that have shaped life itself. Yet the precise mechanisms of its formation remain shrouded in competing theoretical frameworks that seem to defy the conventional laws of planetary mechanics and orbital physics that we have come to rely upon for understanding the cosmos. The prevailing scientific explanation, known as the giant impact hypothesis, proposes that approximately 4.5 billion years ago, a Mars-sized protoplanet collided with the early Earth at an oblique angle, an event of such catastrophic violence that the impact should have vaporized both bodies entirely or sent them hurtling into the depths of space. Yet instead, according to this theory, the debris from this collision coalesced into the moon in a manner that seems almost improbable when examined closely, as if the universe conspired to create precisely the conditions necessary for our existence. The paradox deepens when we consider that this collision would have imparted angular momentum to the Earth-Moon system in a way that current observations suggest should never have occurred, creating a rotational state that defies the mathematical predictions derived from impact models and computer simulations. Yet here exists our moon, undeniably present and gravitationally bound to Earth in a configuration that physics insists should not be possible. We have rationalized this impossibility through decades of increasingly complex models and revised calculations, adjusting our parameters and our assumptions until the theory fits the observations, normalizing what was once considered paradoxical, effectively rewriting the rules of physics to accommodate a reality that our original understanding could not explain. The moon's formation represents a foundational paradox in planetary science, a mystery that we have collectively agreed to accept not because we fully understand it, but because we have no other satisfactory explanation, and so we continue forward, teaching this theory to students as established fact, while quietly acknowledging in scientific literature that fundamental questions about angular momentum conservation and orbital mechanics remain unresolved. Demonstrating how readily we can accept profound mysteries as long as they remain sufficiently distant in time and space. Perhaps the most telling aspect of this acceptance is that we have relegated the moon's true origin to the category of solved mysteries, allowing the comfortable narrative of the giant impact hypothesis to obscure the underlying uncertainties that persist in our models, much as we do with other cosmological phenomena when observation and theory fail to align perfectly. Suggesting that the history of science is not merely the accumulation of knowledge, but rather the strategic compartmentalization of acceptable unknowns. In this light, the moon stands as a monument to our willingness to embrace incomplete explanations, a celestial reminder that even our most carefully constructed scientific narratives contain hidden fractures, and that the universe may harbor secrets far more profound than our current frameworks allow us to perceive, waiting silently in the void for a future generation bold enough to question what we have deemed settled. Yet perhaps this very acknowledgement, that we mask uncertainty with confidence, offers the first genuine step toward understanding, recognizing that the moon's formation mystery is not a failure of science, but rather an invitation to transcend the limitations of our current theoretical frameworks and to approach the cosmos. Imagine standing at the edge of a fundamental mystery that has puzzled physicists for decades, a discrepancy so profound that it forces us to reconsider everything we thought we understood about the sun's inner workings and the very nature of subatomic particles themselves. The solar neutrino problem emerged in the 1960s when scientists began measuring the flux of neutrinos arriving at Earth from the sun's core, where nuclear fusion reactions continuously convert hydrogen into helium and release tremendous amounts of energy in the form of these ghostly particles that pass through ordinary matter almost without interaction. The theoretical calculations were precise and well established, based on decades of stellar physics research and our understanding of thermonuclear processes. Yet when physicists actually measured the neutrinos reaching Earth using sophisticated detectors buried deep underground to shield them from cosmic radiation interference, they consistently found only about 1/3 to 1/2 of the predicted amount. This wasn't a minor experimental error or a small calibration issue that could be easily dismissed, but rather a persistent and reproducible deficit that suggested something fundamental was wrong with either our theoretical models of stellar fusion or our understanding of neutrino behavior itself. The human mind initially responded to this paradox by attempting to preserve the existing framework, proposing that perhaps the sun was cooler than we believed, or that we misunderstood the fusion mechanisms at work, or that our detection methods were somehow systematically flawed in ways we hadn't yet recognized. Yet each of these explanations crumbled under scrutiny as the experimental data became more precise and multiple independent detection methods confirmed the same troubling deficit from different angles. The resolution ultimately required accepting something far more revolutionary, that neutrinos themselves possess mass and can transform from one type to another as they travel from the sun to Earth, a phenomenon called neutrino oscillation that fundamentally altered particle physics and earned the 2015 Nobel Prize in Physics. We have now normalized this resolution so completely that it seems obvious in retrospect. Yet for decades, this mystery forced physicists to live with genuine uncertainty about processes happening in the most familiar object in our sky. This humble discovery, that neutrinos have mass and oscillate between flavors, opened entirely new experimental pathways for studying the cosmos and revealed that the standard model of particle physics, despite its extraordinary successes, was incomplete in ways that continue to inspire investigation into dark matter, the matter-antimatter asymmetry, and the deepest questions about the universe's fundamental structure. The solar neutrino problem thus stands as a testament to how nature often teaches us through contradiction rather than confirmation, reminding us that the most important scientific breakthroughs frequently emerge not from solving problems within our current frameworks, but from the humbling realization that our frameworks themselves require fundamental revision. Today, as neutrino observatories around the world continue their meticulous work, from the Super Kamiokande detector in Japan to the Sudbury Neutrino Observatory that provided crucial early evidence for oscillation, we recognize that this problem's resolution exemplifies how nature often conceals its deepest secrets not through complexity alone, but through the necessity of developing entirely new experimental and conceptual tools to perceive what was always there, waiting to be understood.